So, very good morning, dear participants. I am audible?
Yes, sir, you are audible.
Yeah. So today is the third day of our workshop. So today's speaker is Professor Dr. Pankaj Balkrish Tambe. So just wait. Okay. Pankaj sir, are you there? No? Yes, yes.
Yes.
Okay. So, so first I would like to introduce Dr. Pankaj Tambe, and then he will start giving the presentation. So, Dr. Pankaj is professor in VIT AP University. He is a senior professor, and he is working on uh, nanocomposites, polymer nanocomposites, epoxy nanocomposites, and he did PhD from IIT Bombay, and after that he joined VIT Vellore campus, and he joined VIT AP campus in 2017 as a Dean School of Mechanical Engineering, and so sir having a lot of experience on polymer nanocomposites and published several research articles, and he guided 15 PhD student till date. So I think today he's going to present on lecture on epoxy nanocomposite. So uh, so kindly, Pankaj sir, over to you.
Yes, I can start. No issues. Ambut sir.
Yeah. Yes, sir.
Okay, are you able to see my screen, sir? Ambut sir? Now it's a full.
Yes, sir. It's going to be, but it is not in full screen.
Okay, just I will make it full. Now it's full screen, sir?
Yes, yes.
Okay. Thank you, Ambut sir, for giving a nice introduction. I hope I'm audible to everyone.
Yes, yes, sir. You are audible.
Yes, sir, you are audible.
Okay, fine. So today's, as per today's schedule, this talk has to be given by Dr. Ariful Rahman, but due to certain emergency, he is not able to conduct this session. So Professor Ariful Rahman wanted to talk on the interface aspects of polymer composites, and luckily I have the same research area of the interest. So I thought I will share my expertise in this area, and we have done some collaboration work. So I will discuss that part also. So my presentation is on polymer nanocomposites and its interface aspects. Okay, now, first of all, I would like to brief about what is polymer matrix composites. So we already know the definition of polymer matrix composites, and it's basically consists of your matrix, your fiber, and interface. And we are going to highlight more on the interface. And in this talk, I will concentrate on multi-scale nanocomposites. So I will limit myself to thermosets. But before going into deep about the thermosets, we just know about our polymer is classified into two types, thermoplastics and the thermosets. Okay, a broad classification. And if you look at this schematic, thermoplastics say this is the one monomeric unit, and then all the monomeric units are attached. And here you have a different chains. So basically in the polymers, you have the multiple chains of different molecular weight or different length. So here you see a long chain. Okay. Uh, this is seems to be the amorphous polymer because you are not able to see any crystalline arrangement. In case of thermoset, what is the difference you are observing? Here you have a long chain, and in between two chains, there is a cross-linking agent. So basically in the thermoset, say if you are taking, say, epoxy, you have to add certain amine base hardener, and this amine base hardener will form a covalent bond in between these chains. And once the covalent bond is formed, your this liquid chain of epoxy will be converted into a stiffer solid. Okay, so my concentration will be on the thermosets. And as we know, for this composite, you required a certain fibers and fillers. Okay, so this is the carbon fiber. You might have used also this fiber for your research work. Okay, and this carbon fiber is pretty much used in the aerospace industry. Even your table tennis rackets are made from this composite fiber. Okay, carbon fiber. Now, this carbon fiber and this thermosets, they are processed with various processing technique, and you may get a various product. Okay. Now, what kind of product you are getting? And these are the product. If you see in the marketing websites, say Alibaba, you can see this is the carbon fiber composite mirror product in the automobile. Yes, if someone can afford it, they can use the product, and these products are available in market, even in cars. Okay, the important aspect about the composite material is tailoring the interface. Now you have a long fiber. Here is a long fiber, and here you have a matrix. Here you have a matrix. Okay, now here you have a fiber and a matrix. Now in an ideal condition, what we can assume is the fiber should be very smooth, no surface roughness, and the matrix will be ideally in contact with fiber. But in reality, the real picture is like this. Okay, you have a fiber which is rough. Okay, and the matrix is in contact with the fiber. Now, what kind of roughness is there? So one can use atomic force microscope. And then when you use the atomic force microscope, the fiber roughness appear like this. Okay. Now, the fiber is having a certain chemical composition and matrix is having a certain chemical composition. Okay. Now, this surface energy of the fiber and the matrix, they are different. Okay. And if the surface energies are different, the spreading coefficients and the wettability, it will influence. And of course, the surface roughness also influence the wettability. So if you have a contact angle measurement system, what you can do is you can easily determine the wettability. So this is the schematic. This is all well known. This is the solid. And if the liquid is spread very easily and it is in contact with solid, here you have a complete wettability. This is the ideal condition, which is not easy to achieve because there are surface energy differences. While here you have a solid and here you have a liquid. And of course, the surrounding you have air. And this, what you are finding out, the theta contact angle is 180. So here you have a no weighting. And then here you have a solid and this is the liquid, and that is it will spread over this solid and it will make a certain angle. Okay, so based upon this angle, one can predict the wettability, and there are models based upon this. This theta can be calculated and by incorporation of this surface roughness. Okay, so if you see the initial research on the composite material, they are concentrating on changing this surface roughness or this tailoring this surface roughness and then try to achieve the good mechanical properties and overcoming the disadvantages associated with long fiber reinforced composites. Okay, now what is the failure mechanism in your epoxy long fiber reinforced composite? Now this is the image which I have taken. So if you look at here, you have a fiber, okay, and this is the matrix. And here what you are finding out, this matrix is brittle in nature. Now, and this matrix is brittle in nature, here the crack formation starts. Okay, and this crack formation continue, and at this interface delamination starts. Okay, so the delamination is a major problem in a composite material that we already know. Now, to how to overcome some of the disadvantages associated with composite material. So before going into detail, okay, the one processing method which I wish to cover, because this everyone can make the composite material with the help of this method, and this is the hand layup method. So in hand layup method, what you need is you require the mold. Then what you are doing is here you are just putting say certain layer you are putting of say a polymer layer you are putting, or polymer sheet you are putting. Then you are just placing your glass fiber or carbon fiber mat, and then you are pouring the resin, and with the help of roller you are just spreading those uh, epoxy, and then layer by layer you start making your composite material. Okay, and once your job is finished, what you are doing is you allow the epoxy to cure. Epoxy can be cured at a room temperature, or epoxy can be cured at a elevated temperature depending upon what kind of epoxy you are using. Okay, So I will stick only to one processing method, although there are many other processing methods to process long fiber reinforced composite. So this is what is brief about uh, the long fiber reinforced composite material. Now, what people thought is after 1990s, okay, uh, earlier you have Buckminster Fullerene, and because of invention of a carbon nanotube in 1991, Ijima found, and thereafter research start. At that time, in subsequent year, the clay become peak uh, in its research. So nanomaterials are coming in that decade. Okay, now in this long fiber reinforced composite material, although as there are application in aerospace and automobile industry. Okay, now if you see the high-end cars, you will find out the uh, composite material is already included. Very high-end car. Okay, not our uh, normal 10 to 15 lakh cars, but high-end cars, composite material is already embedded. Now, this delamination is a problem, and people thought, why not to use a nanomaterial which can be reinforced in the epoxy matrix? Okay. Now, what is the nanomaterial? If you look at this TEM, now this is the TEM of multi-wall carbon nanotube. And you will see there are aggregates of multi-wall carbon nanotube where the dimensions, diameter is in nanometers, say maybe 10 to 15 nanometers in the range. And then if you see the length, you can pick any end and then move through this multi-wall carbon nanotubes. Uh, the length is in mm. Okay. Or you can take a graphene nanosheets. So here you have one of the TM image of the graphene nanosheets, which we have reported. Both these figures we have reported in our journal papers. So this is the graphene nanosheets. So if you see the planar things are in microns, but the thickness are in nanometer. So we can say that the material can be classified into a nanomaterial for the reinforcement in polymer composite, where one of the dimension must be in nanometers. Okay, then only we can say a composite which is prepared is nanocomposites. Okay, now what is duty about the carbon-based nanomaterial? Okay, now here you have carbon nanotube. This may be a single wall, and this may be a I think it is double wall, but you can have a multi-wall carbon nanotubes. Okay, or if you have this multi-wall carbon nanotubes, you can cut it and you can convert it into graphene sheets also. Okay, graphene can be prepared by various methods. Okay, nowadays the multi-wall carbon nanotubes are cut and converted into a nano ribbons. Okay, nano ribbons is also nothing but a type of a graphene. Okay, now what is the beauty of these two nanomaterials? Now, if you look at, you take a single walled carbon nanotube or a single sheet of graphene and measure the properties. Okay, the scientists already did it. Okay, and what they have found out that there is a superior mechanical properties, electrical properties, and the thermal conductivity. Okay, now because of this, scientists got attracted. And there is a beautiful thing about the graphene. See, the discovery of the graphene was reported in 2004. Okay, Andre Jim and his student, they have reported. But if you look at the patent literature, uh, we can find out the patent related with graphene in 2002. This is the US patent number, and this is nanoscale graphene plates. And they claim it is cutting off your graphene and multi-wall carbon nanotube, and it can be converted into graphene. The patent owner, Borchong and Wen Hong, also used the patent to coin the term nanoscale graphene plates. Okay, so, so people already know, people worked in a intercalated graphite area and TM image, even in older papers. Uh, no, they have also shown the image of the graphene through TM. Okay, so they say only the intercalated graphite, and they have observed the graphene too. But what is the beauty is, the beauty of Andrew Jim and this, his student, they measured the electrical properties, and then that has created a huge impact, and because of which uh, they won the Nobel Prize. So these two are a very promising fillers, and why it is a very promising fillers, we will see. But any material, if you try to add in any matrix, say nanomaterial, you try to add uh, in a polymer matrix or a metal matrix, there are challenges. Okay. Now, what are the challenges with CNTs? Just I will give you the brief. There is a strong van der Waals forces of attraction, because of which there is a formation of aggregates or bundles. See, if you look at this SEM of single wall carbon nanotube, okay, already the two tubes are very nearer to each other. Okay, and there is a strong van der Waals forces. So it is aggregated. Even the second problem is even the entanglement is there. And you all, as we say, the material has a different surface chemistry. Okay, so surface energy of single wall nanotube and the surface energy of your polymer, they two are different. Okay, so there is a inadequate interfacial adhesion between the polymer and CNTs. Okay, so what people are doing, what kind of strategies they are adopting, they are moving towards a covalent modification of any nanomaterial or a non-covalent modification of material. Okay, so here it is in the schematic, it is given. Okay, there is attachment of certain kind of benzene ring. There is a covalent attachment of some long chain molecule. Possibly here it is a wrapping of your single wall carbon nanotube. Okay, so there are various strategies. Now, you have a carbon nanotube or you have a graphene. The first question which is coming into mind, how to disperse these nanomaterials inside the epoxy matrix. Now, what we did is with one of my research scholar, he already did his PhD under my guidance, Rishikesh Kulkarni. So we started collecting papers related with the epoxy nanocomposites. Maybe it is multi-wall carbon nanotubes, or it is related with graphene dispersion. And based upon this collected literature, we try to see how they are processing the epoxy, especially the epoxy nanocomposites. And once the data is collected, so we have come out with, there are 4 protocols with which the graphene or the multi-wall carbon nanotube can be dispersed inside this uh, epoxy. Now, what are the 4 protocols? See here, the schematic A, SFMS. What is mean? Sonication followed by magnetic stirring. So here in this schematic, this is the probe, which represent your probe sonicator. So here you have a graphene, here you have a solvent, you just sonicate, add inside the epoxy in the beaker, okay, and with the help of magnetic stirring and at certain elevated temperature, you start removing the solvent, and this epoxy and your nanoparticle mixtures, there are certain air bubbles, so you can remove it with the help of vacuum degassing, and you need to add the hardener. Now, once you add the hardener, okay, you need to cast it. You can use the open casting method, and then you can uh, prepare the epoxy graphene composites. So this is the first method. Now here, what you are finding out, the shear energy which is applied for the dispersion is low. Now the next thing what people are doing is sonication followed by the ball milling. Okay, fine. Now when you apply the dispersion with the help of ball milling, what you will find out, the more amount of shear forces are applied. Okay, and you can also prepare the epoxy nanocomposite. In the third stage, third protocol, what you have seen, sonication followed by, here you have a high-speed shear mixer. Okay, so here you have a steel a tip which can rotate it at very high RPM, and then here the shear forces are even more. And the last protocol is uh, uh, you don't require any solvent, but what you required is you just mix epoxy and this your nanoparticle, and just pass this through a 3-roll mill, and with this 3-roll mill, your epoxy and the nanoparticles, they are in high shear forces are applied when there is a contact decrease with in between these 2 rolls, and of course you are getting a good dispersion. So based upon these full data, so we have uh, given the what are the advantages associated with each process, and what are the disadvantages associated with each process, and you can refer this paper online. You can go to my Google Scholar profile, and then you can download the paper also. Okay. So what research we did is we have taken the graphite and we try to exfoliate in the form of nanosheets. Now what we did is we have taken ethanol as a solvent, and since I mentioned the nanoparticle has to be modified, so we have taken one of the surfactant. This is a surfactant name, which is referred as a pluronic, which is a non-ionic surfactant. And this surfactant and graphene is mixed in the ethyl alcohol, and we have probe sonicated. It should be sonicated with the help of ice bath. You have to cover so that whatever the heat is generated, the heat will be removed, so temperature can be maintained. And once you sonication for sufficient time is done, what you need to do is whatever the large aggregate of graphene sheets are there that need to be sediment with the help of centrifuge. So in the centrifuge, you are getting at the top bottom 20%, the larger particles are there of nanoparticles, and better dispersed nanoparticle in the top 80%. Okay, and so we have top 80% supernatant we have removed, and this is the way the graphene sheets are dispersed in the ethyl alcohol. We have taken the TEM image, which shows that yes, here it may look a single graphene sheet, but it may not be single. Okay, and we can achieve a few layers of graphene with this process. Now, our protocol, what we have discussed earlier is sonication followed by ball milling, which we have adopted just for the simple reason these facilities are available with us. Okay, so same thing here. Whatever the centrifuged graphene solution with the help of surfactant in ethanol we got, we mixed it with epoxy. We have evaporated these ethyl alcohol, followed by ball milling, and then hardener we have added, we have degassed, and then open casting method we have prepared the nanocomposites. Now, what we have done is we have taken the TEM of the prepared sample, and when you see the TEM of the prepared sample, this graphene and this is the matrix, and here you have a graphene, and it appears to be a rough surface. Yes, so so that is maybe the wrinkling at this stage when there is a graphene and your epoxy contact, and this has influenced the glass transition temperature. Now, what is the glass transition temperature? The temperature at which your polymers become mobile. Okay. Now here you have a graphene, just schematic I'm just showing so that you get some idea. See, here you have a graphene. Okay. Now when your epoxy chains are in contact, what you see is there are untreated end functional groups. Okay. In addition, here, this droplets is your surfactant, because the surfactant is used to disperse. And in contact with surfactants, also your end functional group of epoxy here, it may be attached. Plus your graphene is forming a interface. And because of this interface formations, you are getting some decrease in the glass transition temperature. Okay, this is done by DSC, but if you use some other method, say dynamic mechanical analysis, then the result may be different. Okay, so we have prepared the composite. We have tested it with the help of universal testing machine in a flexural mode, and with a very low concentration you will see there is a flexural modulus increase and this flexural strength to increase. And why it is increased, you can see with the help of this fracture images, SEM images. So for pure epoxy you will see there is a brittle fracture, because epoxy is a brittle material. Once the crack formation starts, there is no resistance to deformation, and what you will find out this kind of pattern. Okay, but when you add a graphene will restrict the crack formation. So here what you will find out, there is a localized deformation, and because of this localized deformation there is a more resistance to deformation of your epoxy chains, and that is the reason the flexural properties enhances. Okay. And as we have added a low concentration of the graphene, so of course, the thermal stability with the TG analysis, it improves. So this is the paper which we have published in 2017. And of course, we got very good citations. Now, we have just published one paper. This process, again, we try and establish with more nanoparticle and the more research. So what we did is uh, a synthesis of graphene and with the help of the chemical method, and the most now popular become improved method by Professor Tool. And after synthesis of this graphene oxide, we have reduced it. So these are the TEM images. But what we did is last time we have modified with this time we modified is a PV surfactant. Now, what is the beauty of the PVP is PVP is having a good interaction with your epoxy. So what we thought is, yes, now we will try and see uh, the influence of the PVP addition, and then graphene we have put in various concentration. And this time, uh, a chemical method we have used for synthesis of graphene because the yield will be more. Liquid phase exfoliation method, the yield is low. Okay. And it is easy to control the concentration. So what we have seen is with PVP modification, these are flexural modulus property enhances, as well as it enhances thermal stability. Uh, so fine, we have done it with our graphene research. So we thought we can do some research with hexagonal boron nitride, which is also popular. So this is also one of the chemical exfoliation method we have used to prepare the hexagonal boron nitride nanoplatelets. Okay. Now, if you look at the graphene platelets, it can be easily exfoliated, but the hexagonal boron nitride intercalation is difficult, and it's really challenging. Okay. So again, we have used a PVP, and with the incorporation of the PVP, what you can see is uh, at a low concentration, the flexural modulus and flexural strength enhances. And in specific, in this case, HBN, so it is the nanoplatelets, this kind of fracture feature we have observed, and this is referred as facets, which is generally not observed in a pure epoxy fracture. So these two research we have also published with the help of one of my research scholar, Monima Saha, and of course they got very good citations. Okay, so this is the first part of my presentation. So I wish to concentrate on how to process the epoxy nanocomposites. And in the next session, the collaborative work in between the Dr. Ahilful Rahman and me, we will discuss. Okay, so Ambuj sir, shall we take a 10 minutes break?
Yes, sir. We can take 10-minute break. Then we will join at 11. Is it right, sir?
Yes.
Yeah. So, dear participant, we will meet again at 11 a.m.
So we can start now. So in this session, I will cover about the multi-scale nanocomposite and the specific focus on the interface aspect. Now, what is mean by multi-scale nanocomposites? Uh, some people you may see terminology as multi-phase composites. So, multi-scale means two different scales of nanofilter. One is in nanometer and other is in micron size. So you have here a multi-wall carbon nanotube where the one of the dimension is in nanometer, while here you have a carbon fiber, long carbon fiber. The diameter is in microns. So we can easily say this is the multi-scale composites or nanocomposites. Now, this is one of the work which Professor Arifur Rahman headed during his PhD. So what he did is he has received a glass fiber, and what they did is they have heat treated the glass fiber around 450°C, and what they wanted to do is to remove whatever the organic compound which are attached to the surface, because the sizing agents are there, and they have then coated this treated nano glass fiber to deposit a nickel, okay, with the help of electroless plating, and they have calculated the coating thickness, and these are the nickel which is deposited over this glass fiber. Now, why they have deposited this nickel? Because this nickel acts as a substrate for the growth of carbon nanotubes. So what they did is they started growing the multi-wall carbon nanotubes over this coated glass fiber, and they are growing for a different amount of time. So you can see A to I, there are different amount of time. This is a lower magnification image, this is the higher magnification image, and you can see the density of multi-wall carbon nanotube growth. It's varies, okay. And thereafter what they did is in the CVD they have grown it at a different temperature. This is the 500°C, this is the 600°C, and this is the 700°C. And here at 500°C, you will see multi-wall carbon nanotubes. It is deposited, and this the length. Okay, so it is grown perpendicular to the fiber surface. Okay, and here what you can see is there is optimization process they did. What they did is the nickel coating. What they did is nickel coating, the time they have managed and the thickness they have controlled, and then the parameters related with chemical vapor deposition to grow multi-wall carbon nanotubes also they have controlled. Okay, fine. So once this multi-wall carbon nanotubes are grown, now what they did is they have taken a bigger laminate and they have deposited multi-wall carbon nanotube over this glass fiber, and the method which they have used is a pretty simple hand layup method. I have already explained the hand layup method, and followed by the excess is whatever the excess resin is there. So their compression molding machine, they have used it, just apply a little bit of pressure. This pressure, of course, it is optimized. Okay, you can't put too much pressure also. because you need to maintain certain volume fraction and of your epoxy and the filler. So once this is done, and of course the epoxy which they have chosen is cured at little elevated temperature, and finally after that you get the composite laminate. So basically what they did is they have coated a glass fiber with carbon nanotube. Okay. Now once they prepared the laminate, they have done a testing. So this is without growth of glass fiber, carbon nanotubes. The modulus is around 18 to 19 GPa. But when you heat treat it, the Young's modulus decreases because the sizing agent is there on the glass fiber, so it decreases. But on his heat treated fibers, when you grow carbon nanotubes, okay, at 500 degrees Celsius, here you will see there is a remarkable enhancement in the Young's modulus. At 600 degrees Celsius, yes, enhancement is there, but not as much as compared to this one. So if you see the previous slide, at 500 degrees Celsius, here you see there is a denser growth of carbon nanotubes. And at 700 degrees Celsius, it's not too dense. So what you can see is uh, the this coating parameter also influence the uh, mechanical properties of your multi-scale composites. Now, here the fracture feature. If you find out the fracture features, now here this is your without any modification of glass fiber. Okay, so there is no severe deformation at the interface. But when you magnify these epoxy multi-scale composites, at the interface, there is a huge amount of deformation, and that is the reason there is a more resistance and the mechanical properties enhances. Okay, remember one thing. Here, they have not added any nanoparticle inside the epoxy matrix. Only they have just tailored the interface. Okay. Now, what are the issues here? When you see the issues, there are amorphous carbon also. The amorphous carbon content also need to be controlled. Okay. Uh, so this process, they have well established that coating of or tailoring the interface, glass fiber interface, one can achieve the remarkable enhancement in the uh, mechanical properties of glass fiber reinforced composites. And they have published in 2014 in Composite Science and Technology too. Okay. So once I joined BIT, we did some collaborative work, okay, with one of our PhD scholar. So what we did is, we already know from our previous experience that with chemical method, we cannot completely reduce the graphene. Okay, always there are some functional groups which are attached at the surface or at the edges. Now what we thought is, we will reduce the graphene oxide using sodium hydrosulfide. And what we did is, in our earlier studies, we have used NaOH to control the pH. This time we have not used NaOH. We have used simply a sodium hydrosulfide. And let's see what kind of results we are getting. So what we did is, we have synthesized graphene oxide with improved method. Thereafter, we have reduced with sodium hydrosulfide. And we started doing all our characterization. So graphene oxide formation here with XRD, the peak is around 11 degree, and this is a graphene oxide. And when we reduce it, because of the functional group removal, the gap in between two sheets decreases, and with Bragg's law, you can easily predict this 2 theta angle, diffraction angle has to be higher. And we have characterized the graphene. It's appeared in wrinkling at the edges. So we did FTIR, and from FTIR we can see there is a CO group attached, there is a carbonyl group attached, there is a hydroxyl. This OH group is also present over the graphene. Okay. Now, once we characterize this, again we have used the nanocomposite preparation we started. Okay, and this is the method sonication followed by ball milling. The reason is simple: these facilities we have, and we have taken a TEM image. Now, if you see this TEM image, okay, see here, more transmission of light happen because the graphenes are lesser aggregate. Here the graphene are more aggregates. So the aggregations are there in these graphene. But what we wish to say is, now if you look at this scale, here, although the aggregations are there, but there is a breakage. There is a breakage because when you are doing ball milling, okay, you are applying the shear forces, and because of application of the shear force plus the compression stresses will be applied. So in between these two rolls, the shear and compression forces happen, and there is a breakage of graphene. So with the TM powder image of graphene, you see here their dimension is in microns, but after ball milling, the breakage of the graphene sheet happen. Okay, because we need to disperse the graphene. Okay, we cannot prevent the breakage, but we wanted a good dispersion. So good dispersion will come at the cost of breakage. Yes, but what is important is to achieve the desired mechanical properties, whether it is by breakage or it is without breaking, or maintaining its pristine structure in the terms of size. Whichever way it is achieved, what does we want is the mechanical properties enhancement. So we have already characterized from FTIR, graphene has a functional group, and we tried to figure out whether this functional group interact with the epoxy matrix or not. So if you look at this FTIR at 1635, there is a CO stretching. Okay, and 1611, there is a CN stretching. Okay, so this is your graphene, this is your epoxy. So CN stretching is of epoxy, and this is for graphene. And in between these two, if you take a epoxy graphene nanocomposites, there is a shift. See, the shift you may not observe here, shift you may not observe here, but here you are observing the shift here clearly. And this shift depicts the interaction. Okay, now our previous research, we are not concentrate on the what kind of interaction is there in between the graphene, but here deliberately we add more defects in terms of functional group by reducing it with sodium hydrosulfide without controlling the pH. And in this composite material, we have done a dynamic mechanical analysis, and then what we have found out that a glass transition temperature here increases because of random distribution of the graphene, and the mechanical properties also enhanced up to 0.1 wet percentage of graphene addition. And of course, we try to theoretically predicted modulus and the experimental data obtained. So as you start increasing the concentration, because aggregates will be there, and your theoretical prediction cannot match. Okay, so but of course at very low concentration it's matching luckily. Uh, so we can say that with this prediction, we can say that yes, in our matrix, the graphene, there are aggregations. Okay, and this fracture surface, if you see, there is a formation of the facets, and that is the reason mechanical property enhances. And what we have seen is a thermal stability also enhanced at low concentration of graphene. Now we have to move to our next stage. We have taken a glass fiber, and glass fiber has to be modified with multi-wall carbon nanotube. Now I have taken case study of multi-wall carbon nanotube. In earlier work, which we discussed, chemical vapor deposition method was used to coat your glass fiber. But this time what we did is, we take a multi-wall carbon nanotube and we modify this multi-wall carbon nanotube with the help of a surfactant polyvinyl pyrrolidone. Now, what is the beauty of this polyvinyl pyrrolidone? We already know it is having an interaction with epoxy. So epoxy and the interface with your glass fiber, where the polyvinyl pyrrolidone modified multi-wall carbon nanotube is coated, it will interact. Epoxy will also interact, and of course carbon nanotube is there, and with coating they will also interact. So when we take a TM, so this is the TM of pure multi-wall carbon nanotube, huge entanglement. Okay, what we did is we mixed in ethyl alcohol, polyvinyl pyrrolidone also mixed, and we did the sonication. Now, because of this sonication energy, entanglement started, and here you will see from this TEM of PVP modified multi-wall carbon nanotube, there are disentangle, it is well separated. Okay. Now, once we establish that a polyvinyl pyrrolidone can debundle the multi-wall carbon nanotube, we started coating over the glass fiber with a deep coating method. What we did is we have taken one tray where we have put up a glass fiber, and then this PVP solution, multi-wall carbon nanotube PVP solution, of course we have used the water because PVP also can interact. And we have put it inside the tray, allow the water to evaporate, and then in a hot air oven. And finally what we got is over this glass fabric, there is a deposition of multi-wall carbon nanotube. And this multi-wall carbon nanotube in specific is a PVP modified multi-wall carbon nanotube. This is the SEM image we have taken. So this is the bidirectional glass fabric mat, and when we zoom it here, you will find out the rough surface, and then of course the PVP is there, so that is the reason you are seeing a PVP stretch at a higher magnification. So we start processing. The multi-scale composite. So this is the epoxy graphene mixture which we have prepared with sonication followed by ball milling, the very established protocol. And the concentration of graphene we have chosen from our earlier experiment. And we started preparing the laminate with the help of hand layer process. And the vacuum bagging, we have used it, and a little bit of pressure also we have provided, so that the whatever even excess is there, epoxy, it can be removed. So this is the way the multi-scale nanocomposite is processed. So what kind of composition we have? We have a glass fabric epoxy composite, then glass fiber with multi-wall carbon nanotube decorated composites. Okay, here you have a glass fiber with your graphene mixed in epoxy, and combination of both, where the epoxy is mixed with the graphene, and glass fiber is decorated with multi-wall carbon nanotube. And when we see when we tested the flexural properties, what we have observed, uh, modification with multi-wall carbon nanotube do not give us too much enhancement in flexural modulus and flexural strength. Addition of graphene in epoxy, yes, it is giving a higher Young's modulus, a flexural modulus and flexural strength, and the combination of both is giving us the best result. So we try to look at the mechanism why this is happening. Okay, so here you have a glass fabric. Uh, in reality, it's not like this schematic, but it may be some rough surface. And here you have a glass fiber, and this multi-wall carbon nanotubes are here, which is coated. Okay. Okay. Now, when this multi-wall carbon nanotubes are coated, there is the roughness is going to be increased. Okay. And there is a multi-wall carbon nanotubes are here, and so there is a mechanical keying effect is there. Okay, this is the first thing. And if you look at this layer, this particular layer where the graphene is dispersed in epoxy, here you have a random distribution of graphene. So here the mechanical interlocking happen, and because of this mechanical interlocking, these are the two mechanism, mechanical keying and the mechanical interlocking, based upon which uh, we have achieved a good enhancement in uh, mechanical properties. If you see the Professor Ariful Rahman earlier paper, yes, by coating graphene with multi-wall carbon nanotube, they have used they have achieved around 33 or 34 GPa enhancement from 20s. Okay, here we have used a different method, just a simple method we have used. Okay, and what we did is a graphene we have added in the epoxy matrix, and combined effect of these two result in enhancement in the flexural properties. Other properties need to be tested. Okay, so this part of presentation, I have concentrated on the modification of graphene and what is the influence of this dispersion of nanoparticle in epoxy matrix, combined influence, how we are getting a good mechanical properties. And this paper was already published and it is getting good citations. I thank you all for your patient hearing. We can take questions now. You can unmute yourself and you can ask questions.
Dear participant, it's rare opportunity to discuss. If you have any doubt, you can discuss with expert.
Hello,
Yes, sir.
sir. Pankaj sir, am I audible?
Yes, yes. Yes, Ganesh.
Yeah. My question is how this FDM technology can be can accommodate this research related with the nanomaterials.
Okay. See, right now, actually, what I will, the answer which I have, one has to design this machine in a particular way. See, yesterday, the Professor Ravi Kumar, what he has used is two robots, and with the help of these two robots, one can integrate. So I suggest you have 3D printer in your college. Okay,
Right.
you try and prepare certain mechanism. Okay, don't take robot. Okay, it's not necessary to design a robot and then do it. Okay, but you prepare certain BTech project, certain mechanisms where the deposition of or layering of your glass fibers rolled are available and it's pretty cheap. And then you how you are just making a one laminate and how it can be placed. Don't take a ready-made one, because with the ready-made one you can easily place it and then integrate it. You try and deposit your ABS or PLA and then compression mold it. That is the easiest way, but that won't give you many papers. Maybe one paper you can get a conference paper. That I think I will suggest you to prepare a one different machine, and then a simple setup, and then how to deposit your glass fiber on one layer, and how it can be transferred to your FDM, and then you deposit your polymer. It may be your photopolymerization method, or uh, your in that case I will say suggest you thermoplastic based FDM, and then of course you can play with orientation and modification. So there is a huge scope for research.
Right.
I hope I have
And-
given certain direction.
Right. And second question is related with the SLA technology. Okay, where we are using the liquid-based material. In that condition, in that particular form of material, how this combination of polymer material and the nanomaterial or nanotubes, this can be done.
Okay, fine. See, in case of polymers, so photopolymerization is there, so there is no need of laser, but you require a UV lamp. Okay, those setups are available in the market, but the problem with those setups are you have to purchase a particular type of epoxy. So photopolymerization is again preparation is again a challenging one. Okay, so you required a chemist to do that. So what I feel is your question is related with SLS, and that too for
SLA.
oh, fine. I think SLA. Okay, fine. In that case, you just look at this SLA. What kind of opportunities are there? So best thing is whatever the resin and whatever the material, polymeric material they are using. Okay, you try and disperse the, if it is uh, the methodology which I have given, dispersion methodology. So
Yes, sir.
with that, you try and disperse your nanoparticle, play with interfacial aspect, and then go ahead with your 3D printing, and then further research or make a component.
Yes, right, sir. Thank you.
afternoon, sir. Good morning, sir.
Yes.
I have one doubt, sir, here. You have tested for the static mechanical properties like flexural modulus, all these things
Yes.
based on the coating, sir, either on the fiber or mixing with the epoxy, your CNWTs or the graphene.
Yes.
What about the dynamic mechanical properties of these composites?
Yes.
Made
Yes.
up of,
Fine. See.
yes.
Okay, fine. I understand your question. See, if we try and do the fatigue testing, one has to see. One has to be a little careful. Now it is going in a dynamic mode. Okay. Fine. So, for establishment of product made with this multi-scale composite material, the whole range of testing in static and dynamic range has to be done. And once it met the requirement as per design, then only this can be deployed. Okay. So basically what we do is whatever constraint we have, based upon that, see CVD, the problem is you required a heat treatment. And once you do heat treatment, thereafter you have to deposit. And of course, every machine has the issues. Here we have used the water as a solvent, which industry can use it. And there are a lot of optimizations need to be done. Yes. And so for as what result we reported, after fatigue testing, we may not get maybe the desired result. One has to do test and then what are the other requirement, whether the multi-wall carbon nanotube concentration of coating need to be controlled. All these aspects will come into picture, and then only one can recommend this material for the industry. So why we publish a paper, because it is giving a certain directions for the growth of the area. I hope I have given you the answer.
Is there the coated fibers available in the market, sir? Nowadays?
Okay, coated fibers. See, I prefer to do the coating on my own.
Okay.
But even getting a glass fiber coated sample is difficult.
Yes.
Okay, because you won't get in
So
the market.
we need to have
You need to. It's difficult. You don't get in the market. Okay, because there are other issues. Once you start coating it, you have multi-wall carbon nanotube where graphene is coated. And once you started shifting it to a different location, and there will be another issues. Okay, the loss and etc. So no one will going to sell it, coated fiber. The process has to be established in industry and then manufactured. So you have to coat, and that is the reason I have taken this particular case study, and to show that yes, in a lab scale also you can do it, and it's pretty simple.
The same multi-scale nano composite we can follow in the metal matrix composite also, sir.
I see, to my knowledge, see, there are ongoing research effort in hybrid fillers. So what hybrid filler people are doing it, okay? And then if you are, so just you have asked me, so what you can do is a chopped carbon fiber you already got, or you can chop glass or glass carbon fiber. You try and coat it with your nanomaterial, maybe a multi-wall carbon nanotube. Nowadays it's pretty cheap, and you need to add a very little for coating.
Is there only these two nano materials, sir? Any other also available?
Availability is, there are huge range, ceramic based, carbon based, clay. It depends what kind of applications you are looking at. Say if you are looking about the improving of the wear resistance. So people are adding your ceramic based materials, titanium based nanoparticles. Okay, so it depends upon your choice, and it's complex. Okay, so that is the reason the hybrid.
Yes,
Fine.
sir. Yes. Thank you, sir. Thank you.
So Abu sir, then can we wind up this session?
Any other question, dear participant? Okay, if you do not have any questions, so we can wind up the meeting. And sir, we will meet at 12, which,
1 o'clock.
1 o'clock for next session. So thank you so much for joining the session, and we will meet again at 1 p.m. 1 p.m. Yes. Mhm.
Okay, good afternoon, Akash.
Pankaj, good afternoon.
Okay. So we can start at 1 o'clock.
Okay.
Okay.
No problem, because just I will share my screen just to see that.
Okay.
So my screen is visible?
Yes.
Okay. So,
Fine. Then we can start at
And-
1 o'clock, sir. Okay.
my voice is audible, is clear?
Yes, very clear.
Okay.
Okay, sir. We can start at 1 o'clock, sir.
Yeah, exactly, I will start at 1 o'clock.
Okay.
I am ready.
No, I will introduce you, sir, at 1 o'clock.
Yes,
After that we can
okay.
start. Okay.
Hmm.
Dr. Akash, can we start?
Yes, you can start.
Okay, so first of all, I will introduce you, okay? So good afternoon, everyone. Welcome for the today's session. So I think I will first introduce Dr. Akash Mohanty. Dr. Akash Mohanty is currently Associate Professor in School of Mechanical Engineering, VIT University, Vellore. And we both joined together in VIT University, Vellore in 2010. So we have a very long association. And Dr. Akash finished his PhD from IIT BHU. And he worked extensively on composite material. In addition, his interest lies in finite element method, even fracture mechanics of composite material. And he has published many papers related with composite material and which are fetching good citations. He has guided, is guiding many PhD students. And with this brief introduction, I hand over the session to Dr. Akash Mohanty.
Thank you, Dr. Pankaj. Thank you for a nice introduction. Welcome to this workshop and good afternoon to all of you. I hope my voice is audible. Is it? My
Yes,
voice
yes.
is clear?
Yes, yes.
Okay, thank you. So now my topic is epoxy nanocomposite. So these two words are totally, both are different. One is called epoxy, one is called nanocomposites. So here, all of you are attending this seminar for last 2 days. Many things already it was told to you by so many eminent professors about the polymer composites. So in the polymer groups, there are basically two type of polymers. One is thermoplastic, one is thermoset. So here, thermoset, in the group of thermoset, epoxy is widely used because of its excellent properties. Okay, so along with these excellent properties, some disadvantages also are there. So unless and until we will overcome this disadvantage, we cannot produce a quality substitute materials for advanced engineering applications. Okay, so whenever we are discussing, our main objective of attending this workshop and seminars is that to understand, to get some knowledge, and so that we can start our research, and we can extend whatever we are doing at the present time in this research work, and we have to publish the paper. So whenever we are discussing about research work, these words are very common, that we have to do very hard work and we have to choose the hot topic. So these two words, actually my presentation is not for hard work. My presentation is for smart work. How the same output we can get after eliminating so many complex procedures. Because our life and our working environment is very complex. The composites itself is a complex subject. So I believe that if you are entering into the complex field, why you will not think about a process which will be easily adaptable and we can get whatever we want. So the main purpose, I am not telling about any new thing, but I am supposed to tell about the same thing, but approach will be little in a smarter way. That is the main purpose of this presentation. So here, epoxy is not a new topic, nanocomposite is not a new topic, but the same thing, whatever we have already listened from our previous eminent speakers, they have enlightened so many processes. So we will do the same thing in a simplified manner. So that is the main objective of this one, this talk. So here the objective is, I have already told, for the simplification of this process. So simplification does not mean that we will compromise the quality. So quality should not be compromised, but the method of approach will be slightly modified. So that is the main objective. So in introduction, we require smarter material for high-end engineering applications. So we require new and more best quality products. So all the research is directed for this purpose only. So here, whenever we are talking about the nanotechnology, nano, so whenever you are going to 10 to the minus 9 meter to that range, so the main problem is that the dispersion. So dispersion is a very, very difficult task, because whenever you are going to nano level, the surface energy increases tremendously. So since the surface energy is very, very high at nano range, so dispersion is a highly challenging factor. And next is that the fabrication method requires homogeneity structure, so that everywhere you can guarantee that the property is uniform. So due to that, these are the challenges which we have to overcome in a smarter way. Then after doing this one, we have to fabricate the specimens, and we have to do the rigorous characterization, mechanical characterization, because this topic is taught. I am giving the lecture to the Department of Mechanical Engineering. So for that purpose, we require structures. So structures require energy, it require strength, it requires stiffness. So for this purpose, from molecular level test, thermal and electrical, all type of tests are also embedded along with the mechanical characterizations. So whatever results are there and what is the conclusion. So before that, what I want to tell you that in this nanotechnology, there are so many research are going on, particularly carbon nanotube, graphenes, and particles in nano shape. So in that range, alumina plays a very vital role. So in this, alumina is also previously used and published. So whenever we want to do the research, we have to use our brains in such a way that we can penetrate in the well-established field. So here, what I have thought that let us take this alumina, special grade of alumina, which is already used, people are already acquainted, and let us take thermoset resin. So in thermoset polyester epoxy, so epoxy is widely used. So let us enhance this one so that we can go for some useful product to the society first. Also, we can penetrate to high-end publication. That is the main objective. So in this study, so the alumina particles was taken, and also since we are talking of structural composites, so in the structural composites, the biaxial fibers are there, but here I have taken because my objective is to prove that something is happening. We can increase the strength of the final product, that is your composite. So for this, I have taken the short glass fiber and short carbon fiber, because the mixing will be easy, so that you can study the improvement of the properties of this final product in a simplified manner. So for that, whenever I am talking about improvement of the property, that is your mechanical or maybe electrical, all series of property, whatever is essential to develop a product, output product. So it is required this type of property like thermal property, rheological, tribological, all type of things we have to study. We have to see what is happening. So then whenever you are talking about these fillers or reinforcing elements, so we should optimize one point, because it is not like that you keep on adding and property keep on increasing. It is not like that. That is a threshold values. So as the type of ingredients will vary, the threshold point also will vary. So that is that point where we have to target. So these are these main points. So here in this here in the extension of introduction, so we require classic materials, and we require nowadays, all people are saying that composite and hybrid composites are taking the markets, and what are the various characterization techniques are used, and what is our output, what is our objective. So since in this case we have taken the epoxy as our raw material, because it is highly used in all industrial applications. So this epoxy we have taken. Then the glass fiber, chopped glass fiber already is there, and carbon fiber also it has procured from Joltech US. And the magic of this topic, this research lies in this powder. This is called alumina powder. This is not a new thing here, but the process is something other than the whatever of traditional method. So this is the main key factor of alumina powder, where I have procured from Germany. Sasol is the manufacturer. So this is the manufacturer has supplying this powder in a macro size, micro. Okay, so that I have procured, and there is some properties are also there. I'll show you. And the Joltech fibers, whatever I have taken. So density is and the fiber length, whatever size, and all the information here it is given about this. Then a little bit about this epoxy matrix. I hope that most of us we know that. But to continue the talk, I have added this slide that epoxy is a epoxide plus polyamide. Whenever this hardener will be added to epoxide resin, so we are getting the three-dimensional pure product that is called epoxy. So again, epoxide is epichlorohydrin plus bisphenol A. So these are the structures, and whenever this amine-based hardener is added, so we are getting a permanent and cured three-dimensional product. So this is our case, a resin plus hardener, and this is your cured polymer. So they will entangle permanently. So here the resin we have taken with PL411 and hardener is 861, and these are the specific gravity 1.14 and hardener specific gravity almost equal to water. So 10 to 12 weight % we have added. So here some suppliers data we are getting, the epoxy modulus, alumina modulus, glass fiber and carbon fiber, Poisson's ratio and density is varying. Alumina has a high density. So here, what is the things, what is there in my mind, why you are approaching this one? So here, whenever we are talking about the curing process, so in the curing process for the polymer is a very simple one. So we are taking resin and we are adding hardener. So during this hardener, amine groups react with that epoxide groups in the resin. So they are making a bond, which is called covalent bond. So each NH group of our hardener react with that our epoxide group, and it develop a high strong cross linking. So once cross linking is developed, so we are getting a strong product. So here then this is the basic mechanism, curing mechanism of our epoxy resin. So alumina, whatever we are taking as our ingredients, so this alumina particle contains pure alumina, Al2O3, 69.2%, little bit carbon, and this has a very high surface area, 265 meters square per gram. It is a powder, so it has a loose bulk density of 0.42 gram per mmq, and there are, you see here, when I am projecting you the alumina particles of the size 25 micron, it is 12.5%, and less than 45 micron, I am using this word micron, not nano, it is 15%. Then particle size less than 90 micron means it is increasing. So 46% of this particle, alumina particle, what I am using in this research work is 90 micron content, almost 50%. Okay, so here dispersibility in C2H4H5OH is 98.3%. So here then I am talking about the nano composites, but I am using the particle which is micron size. Then you will think that since a nano word is used, maybe the fiber will be nano size. No, it is not. Fiber is not in nano size because fiber size in mm. Then what is the things are going on? So the main thing is that whenever we are going for this post curing operation, all the mechanism and curing things, all the mechanism will play the vital role of this researcher. So what is the curing cycle? First, it happens in a stepwise manner so that we can get a proper, three-dimensional rigid structure. So this is the diagram. The y-axis is temperature and the x-axis is your time. So in stepwise, it is cured. So it is just below near to this 100 degrees centigrade, and it has cured like that, stepwise, step. So that why we have followed the stepwise, so that we are giving enough time to complete the reaction. The chemicals should complete its own chemical reaction so that we can get a proper and a rigid product. So here, so whenever we are talking about the improvement of the mechanical properties of the resin, so there are so many approaches are there. How to develop the resin, because this resin is a matrix. So whenever we are applying this load, whenever we are talking about any composites, polymer composites or any composites, you take as a roof is a composite, our bone is a composite. Similarly, whenever we are talking about FRP composites, the main load carrying element is our fiber, or the non-continuous phase elements are main load bearing members, but that is required another continuous phase material which will hold all this reinforcing element into its own position. So whenever load is applied, the load first catches the fiber. So fiber to next fiber. So it travels through the media, that is called your resin or matrix. So this matrix plays a very, very important role. Now, whenever we are talking about the improvement of the property, we will procure the fibers. We will procure the base resin, epoxy resin. But whenever you want to develop the property, nowadays it has come, let us grow the carbon nanotubes in the transfer direction, and you do some chemical treatment, improve the surface property of the fiber. These processes are very, very critical and complex. So whenever a person wants to enter into a field, so the system fiber itself, this world is itself is a complex world. Again going for the treatment, then again going for the growing up the carbon nanotube, the transfer direction of the fiber. This is also a very big challenge, and it will add more cost to the equipments, whatever you require. For most of case, we don't have that facility. Those people are very lucky, or if you will go to that segment, you will always run behind for high-end machinery, CVD, like that. So that what they are doing, what is the purpose is that they are making the surface rough so that the bonding of your resin to the fiber will be more, so that more energy can be transferred. But the main challenge is here is that whenever you are coating or you are growing the carbon nanotube on the surface of your fibers, how to ensure that the property is uniform through all the corners everywhere. It is a very big challenge, which is to be dealt in another time of presentation. But here it is a very, very challenging thing. So it is increasing the complexity of our process. But our main objective is that after growing your carbon nanotube, whatever property we are improving, with a simple method, we also produce more than whatever you are getting. So that is the things, it is our challenge to see this one. So here, this is one method that chemically you modify the epoxy. So if you modify means backbone, you have to add some another chemical agent so that it will become the more flexible, and the ductility property will be enhanced. That is a chemical modification, where the chemistry people, they know more about that. But here the another thing is that increasing the molecular weight of your epoxy or lowering the cross-linking density of the material. These are all chemical modifications. Then another approach is there, which the chemistry, these people, they know all about. But being a mechanical, so what is another things are there? We can incorporate, or you can dispose some top end phase, top material like a diamond, or like our alumina, like that. we can use this one so that we can toughen the matrix, or by the incorporation of inorganic filler into the net resin. So whenever we will introduce some inorganic fillers, it will create a strong polar bonds. So these strong polar bonds enhance the property or quality of the resin. So this resin is the main factor where we can expect some improvements because it is in our hand. So the alumina, whatever was developed by Sasol, it was for some other purpose. So what I have thought that why we will not take these particles and we will do this type of things in our field. So here what happened, what is the mechanism, what I have planned here is that first the particle whatever I have taken, we have chosen for our study is in micron size. So 90 micron, up to 90 micron also it was there. So whenever we are using this method, our only one objective, which is very, very clear, that how easily we can produce efficient results without going for complexity. That is our only one objective, so that we will get better product, high energy product, and we can produce the good quality papers. So here if you go for the, if you take for the nanoparticle, so this nanoparticle have more surface energy. So whenever there is a more surface energy is you are dealing with, the mixing is extremely difficult. It is very, very difficult to mix. So you have to go a very, very rigorous method. So it is deal with your high-end machinery, high cost, and you know in our countries whenever you will increase your complexity and your self problem will arise. You will not get proper help. Some people may have the machine, they may not also help you to carry out your experiment. So there is so many practical problems are there. So we have to approach in such a way that we can minimize the problem, so that we can proceed in a smarter manner. So in this case, whenever we are taking here this particle, this alumina particle, it is a process technique which this such a company has done. So that particle was taken whenever it was mixed with our epoxy. So I have not gone for any high-end mixing method. It is simple, very simple. Just take a resin and then you take this powder as your whatever you want. Then simply take one that glass rod and simply you mix as if you are mixing sugar with your water. So it is a very easy method, anybody can do. So then how this mechanism works? So whenever the hardener is added, this is the exothermic reaction process. So here, due to exothermic process, the hardener, whenever it will react with the resin, epoxy resin, so it will develop a lot of heat, and after that it will shrink. That is called curing. So whenever you are mixing this one with our resin, you are applying some mechanical energy. So mechanical energy should be simple one. Either you take a glass rod and you mix, or in a magnetic rod and stirrer, so that the process will be very simple. Anywhere it will be available. Or else take on a glass rod, take a beaker, pour this particle and take a glass rod and mix. So it is a simple process. So during that, some of the particle will break due to external mechanical force. Okay, so the remaining, what will happen whenever the reaction will start, whenever you are adding this hardener to the epoxy matrix, that your solution, so due to heat, so the particle it will release, it will weaken the whatever bonding of these particles with adjacent to each other. Then curing. So curing is a compressive force. So curing means it is contracting. So during that internally, because first you have mixed, that is not a very big technology. Simply you have mixed like sugar was mixed with water, like that. The particle, alumina particle was simply thoroughly mixed with our resin. Okay, then you are adding this your hardener, and you are keeping for your molding purpose. So during that, heat and compression is happening together on the resin which contains alumina. So inside the container inside the resin quantity, the entire big process was happened. So due to contraction at a high temperature, the macro size particles broken into nano size. You are getting? So here the particle size was 40 micron was converted to 20 to 500 nanometer. So now without taking any stress, without going for any rigorous treatment of growing carbon nanotube coating and this that, simply without disturbing anybody, very simple way you mix the particle and it was converted into nano range. So this is a pictorial demonstration how it was can be converted. So stage 1 it was as supplied alumina. Then during mechanical mixing, so it will slightly it will break. Then during the chemical attack, during this curing process, it will stage 3 we are going for our nano size. And this is so sophisticated way it was happened that it will give you 100% guarantee the uniformity in the property, because it is happening in the liquid stage and it was cured. So it was 100% guarantee can be given that wherever you do the test, the property of this mixing is uniform, which is impossible to give guarantee if you go for any other method for growing carbon nanotube in the fiber or coating. Whenever you will coating, there is a practical difficulties are there, physics is there, where giving guarantee for every entire surface is very difficult. But here we can give the guarantee the matrix which is containing this particle in nano shape is dispersed uniformly everywhere, because it is happening in its liquid stage. So after this one, whenever you are going for our fiber, you can add your fiber. This matrix can be used as a matrix material for making three-dimensional. You can use fiber as a mat or a small chord fiber. So whenever you use, that is called a hybrid composite. So whenever we are talking about that, there is so many methods tests are there. So it requires some procedure casting. These are the things whatever I am showing. I will go fast. So here these are the things what I have used to prepare the cylindrical specimen, because we may require for our compression, because it's required as per the ASTM standards. So as per that, the metallic molds are here. And as per the requirement, we can use this type of metallic molds and we can make the specimen. So other type of test, rheological, mechanical, thermal, like that. Then here we can also do some, because our objective is to challenge this field, so that the regular test which is already done to confirm the property of the polymer material, I also follow the same technique, so that we can conclude that yes, this is the technique we can also adopt for our property enhancement. So all the things which is very common to our polymer field, all the things, dynamic mechanical analysis, everything it was done, so that we can pinpoint the development of this product, of this material. So our objective mechanical product having a higher strength, so all mechanical tests also was carried out. Then for more, after doing the test, it will fracture to explain the physics behind that. Some other tests are required. So same and optical microscopes, microscope was taken, that some images are there. Then also, why not electrical property you should not check? Because whenever electrical property you are talking, it is also passing through the matrix. You are saying that I am developing the matrix, then let us see how it is doing, how it is the voltage breakdown potential was improved or not. So it is an electrical test, so it was done. So there are so many tests, because it requires rigorous because we have made this system so easy that we can go for any number of specimen, and we can go for any number of tests. So lot of experiments was done. So sometimes we are always talking about the testing of the material. But whenever we are pulling something or we are crossing something, we are throwing the residue. But many times the residues are the signature of the property of the given material. So this residue also tells so many things about the strength of your composite. Suppose it is very strong and that it will not fail. These are all failure components. But when the failure, by looking the failure of your specimen, this side, this is brittle failure. But after that, the property was increased. So the failure is not that this one is failed, but it has not segregated into n number of pieces. So due to that, the stress strain curve will give you the longer period of time where the energy absorbed to break the specimen is more than the pure epoxy specimen. So these are the tests for flexural you know all about. I don't want to repeat whatever you know already, but what is new to us that I want to focus. So this is called electrical, that is called the breakdown test, electrical breakdown test. This is a very critical test and it was conducted in Department of Electrical Engineering, IIT BHU. So here it was this setup I have developed this one. So these two anode and plus and minus current will be passed here, and here how it will fail. Once it will fail here, it will blast at a higher voltage. Okay, so here it will, this is a failure component, and these are the things where I have tried in number of ways, because this was no one was there to refer. So here I have tried by myself. So many previously I have started here. So this whenever you will increase the voltage, it will spark go here and it will join here. So it was a failure. So then I have tried with this one also. So it is also happened because we are going for 33 kV. It's a very high voltage. So I have increased the surface by using this one. So many permutation and combination I have tried. Then whenever you are talking about I am saying that the supplier I have taken in micro size and it is converted into nano size, but how you will believe me? So for that, we need some confirmation test. So confirmation test should be done in quality lab. So I have done this SACS small angle X-ray scattering experiments. So in that small angle X-ray scattering experiment, it was found that the size of this alumina particle was transformed from micro size to nano size, and the average size is 25 to 32 nanometers. So this is a instrumental data, and it is giving that is some calculations are there. So finally they are concluded the size was this one. So that means it was saying that I have taken some different up to 4%, and then after 5% onwards the particle size was increasing. Okay, so here if you ask the question, I will explain more. So here first thing is that we confirm that yes, whatever was we have thought, it is really happening. That was very big challenge before starting this experiment. Then this is instrumental data, but nowadays we have to believe. Let us see. I will tell this is a pen. You have to show yes, this is a pen. So for that purpose, I have done the transmission electron microscope test. So here I want to see visually in my eyes and to measure this dimension whether it is coming under nano range. So 1%, 2%, 3% like that, and 5%, 10% like this. So here these data are giving how if the agglomeration is increasing, if your weight percent of your particle is increasing, then agglomeration also increasing subsequently. So here this is our pure data, because if less number of particle will be there, so there will be matrix failure will be there. If more number of particle will be there, there will be agglomeration, air void, so many other concept will come. So due to that, I personally have taken. Then I thought that why whenever we are adding this alumina particle, whether there is any chemical change in the bond at the bond level is happening or not, it was not expected, because it is just it should not be there, but one confirmation test should be done. So here I have taken different percentages of alumina for my personal study. So here I have observed that there was this peak sheet here. It was not too much. Almost it is same for all up to 5%, because 31.8 and 32% is it cannot be considered to be a very big sheet. So here it is 50, all are 50. So that means alumina is not very much reacting to the epoxy at the molecular level, or not molecularly it is reacting. So then FTIR, whenever we have done here, so for hardener, because resin we have to take hardener, then whenever this composite here, means your cured epoxy polymer, then after adding 1%, 2%, 3%, and 4-5%, and after adding carbon fiber also, let us see what is happening. So here, this is our common combined data, which is here exfoliated. So here it is combined data. So here, this is the graph of epoxy, and this one is our epoxy with alumina. So all the points, whatever peaks are there, it is also showing. So what is we are observing here? In NMR, we saw it is not reacting, but here in FTIR, it was the stretching of bonds was observed. So OH bond was stretching occurs at 3500 cm per cm. So here the CH bond stretching for CH2 and CH3 was also observed at the different points. So here, what I want to say here, the wave numbers are also in x-axis, so I have marked here. So these wave numbers are giving the stretching of different band. So Miss OH also stress, CH bond also stress, C double bond C. These are the things why is responsible for the enhancement of the property of a composite. So here we have confirmed that yes, the property, if it is increasing, and these are the factors which is responsible for this. So then dynamic mechanical analysis we have done here to understand the property in a dynamic state. So here 3-point bending machine was used, and we have studied the dynamic mechanical properties. So dynamic mechanical property mainly for storage modulus and loss modulus tan delta. Okay, so here the neat epoxy, then 2% alumina, then 5% alumina whenever it is mixed, because one is our 2% and one is 5%, both are we have taken. So this is our, so that you can see the clearly, you can see the, because all the graphs are taken, but I have showing you two so that we can see very clearly. Otherwise all the data will club, we cannot understand what is really happening. So whenever you are adding 2% alumina, so this is the last one outside, and the intermediate one is 5% alumina with epoxy. So from this one, what we are getting, the whenever you are adding to this our alumina particle, the storage modulus increases. Okay, so the best result we are getting when 28% of alumina is added to the than the 5% nanoparticles. So here the nanoparticle contain 28% alumina exhibit remarkable increase in the storage modulus due to better dispersion of alumina nanoparticles in nanocomposite. So this better dispersion, it has proved in our previous test. So loss modulus also is like that. Similar trend also for 2% it is here it is showing neat epoxy, then it is our alumina is intermediate, and next one is our 2% alumina with epoxy. So this is our loss modulus. So what we are getting, the temperature peak at near about 60 degree is corresponding to the transition of epoxy component. Due to the presence of alumina, the transition peak of the nanocomposite increases as compared to the neat epoxy, indicating the restriction of chain mobility due to the presence of alumina nanoparticle. Then the remarkable transition peak shift of epoxy containing 28% of alumina is observed as compared to the neat epoxy due to well dispersed alumina nanoparticle without aggregation. Okay, so due to this we can understand, okay, yes, it is working. Then XRD we have taken. So here XRD different peaks are also available. So here it is intensity, relative intensity in y-axis, and the angle 2 theta in your x-axis. So XRD peaks of micron size, here you see we have taken pure alumina, this one in below here, last one, this is your alumina. Then over that it is our epoxy. So whenever this alumina is added, so it is showing some here, this peaks are, it is visible at its predetermined places. So here XRD spectra of micron size alumina exhibits characteristics peak at 14 degree, 28, 38, 48 and 55 degree, while epoxy show the characteristic peak at 5 degree and 17.8 degree. However, the XRD peak of epoxy alumina nano composite depicts characteristics peak of alumina at 28, 38 and 48 degree, 48.9 degree respectively. With increase in weight percent of alumina particle, the intensity of the diffraction peak of alumina in epoxy alumina nanocomposite decreases, while the width of the peak, it may be due to the reduction of the micron size alumina particle into nano size of alumina particle during our curing process. So similarly, some other people also, they have tried. What they have done, they have taken the micro size particle, but externally they have converted into nano. They have tried, but here whatever is happening, it is happening inside the material. So this is our DSC test. So this is a very characteristic test which gives some information about the stability, thermal stability of your material. So here this is the temperature versus time. So this is for 2-8% because the 2-8% have a better dispersion. So this graph was shown other than the other graphs. So this is as this is called y-axis temperature, x is time. So as time increases, how the stability and final decomposition we are getting from this diagram. Then TGA analysis. So this is also TGA is another standard test. So here we are getting this decomposition of your material. So here this is your more clear. So 0% aluminum is pure alumina, pure epoxy. There is no any ingredients. Then the filler materials are added subsequently, like 1, 3, 5, like that. So here we have found that whenever you are adding this filler material, this curve is shifting towards right side. So here the decomposition region is centered between 270 to 6. So here to here, 270 to here, it will go upward. So up to here, as temperature is increasing, so it is containing 100% means on our composite or material, your material. As temperature is increasing, so it is degrading. So where it is the range here, it is available here 270 to 460 degree. So when you are adding 1% of aluminum particle, the curve is shifting towards the right side. Okay, that means thermal stability was increasing. Further increasing the concentration of alumina in the epoxy nanoparticle result leftward shift. So this is the main point I want to show you. It is not like that will keep on increasing, it will keep on moving, thermal stability will improve. But if you add more particle, so it will come backward also. So there is a optimum threshold value, you can go for that. Beyond that, you cannot keep on adding and you cannot get more properties. So here we can understand that at lower percentage, we are getting for 1-8%, 7 degree advantage we are getting. And whenever you are getting, we are adding more than 5%. So the TJ curve shift towards 5 degree and 8 degree respectively for 3 and 5-8%. So that means 1-8% we are going right side, 2-8% also will go right side, and 3 and 5 is coming back. That means some agglomeration, something is there. Then AFM, atomic force microscope, we have taken to understand the particle size and all, and surface roughness also. In surface roughness, whenever you are taken at 2-8%, since the dispersion is better at 2-8%, so this type of behavior, it is proved that the 2-8% is the best choice for making this type of material. Then HDT HDT test was carried out. So here, so up to, because HDT test is a depression test at a height with the increase of the temperature. So as the alumina particle was improved, was increased, so it will become very steep and resistant to the heat penetration was maintained constant. So it is just one type of, to give some idea, I have done this. Then mechanical characterization. So in mechanical characterization, I think I have 5 minutes time. So this is our main analysis. So whenever you are adding these particles, so you are getting, so first one here is your carbon fiber, glass fiber, and alumina particle. So whenever we are making the matrix as stronger, then the property at weight percent of the filler. So here tensile strength, and this is a weight percentage of the filler. So here neat epoxy plus alumina particle, carbon fiber plus epoxy, glass fiber plus epoxy, carbon fiber plus 28% alumina. So you will see the 28% of alumina particle in the matrix with the carbon fiber will give you the best tensile strength. Similarly, the same thing also, carbon fiber with 28% our alumina particle, it is giving more modulus, highest modulus of this combination. And also in glass fiber also we are getting similar trend. So here glass fiber, it is higher than the simple glass fiber. So it is increasing. So this increasement is due to the enhancement of the matrix property. Then this is our mechanism. Then how it is happening? This is a pictorial demonstration. Whenever there is no particles are there, so this is a fiber. So there is a nearest to the fiber, that is called interface. So in the interface, whenever you are adding nanoparticles here, so whenever crack is proceeding towards fiber or from fiber to this matrix, so it is going through a continuous medium. So whenever it is going through a continuous medium, so what is happening, due to there is no obstruction, so crack propagates very quickly. So if there is a lot of obstructions are there, the crack energy will be absorbed. So throughout, so that I thought from the fracture mechanics, this may be the case. So when more energy will be absorbed, so the strength of the material will improve. So that is our comparison test. So this is your mold and this is specimen. So here the glass fiber and carbon fiber containing 2% of alumina. So it is giving these two here. This is in this side. Both the cases they are giving more strength in compression than the pure one. Here this one is epoxy, not alumina. This is your epoxy. So first is pure epoxy, then glass fiber, your epoxy fluid with glass fiber, epoxy with carbon fiber, then epoxy plus glass fiber plus 28% of alumina. So like this we are getting the improvement in this case. So 28% epoxy plus 28% of glass fiber and epoxy plus 28% of glass fiber, 28% of alumina. So wherever there is a alumina was there, so the property is improved. So here these are the cases. So this fracture test specimen. So this fracture test specimen, if you look at very carefully. So whenever we are adding the nanoparticle, 28% nanoparticle, than the 0 nanoparticle, that means neat epoxy. So if you see here picture number A, so it is purely brittle failure. So whenever you are adding these nanoparticles, the brittle nature of the matrix was reduced. So brittle nature was reduced, that means it is ready to take more energy to completely fragmentation or complete failure of your specimen. Then if this is the case, these are called low velocity test. But here suppose you will go for impact test like that. Here also I have taken for randomly glass fiber 10% for personal study. But whenever we are naturally, whenever we will put the glass fiber, carbon fiber, the Charpy strength with angle of orientation of the glass fiber also it will be changed. But whenever we are talking about our this analysis is for your angle of orientation. Okay. But main thing is that our whenever you are using the here, whenever you are using 28% of alumina nanoparticles. So in both the cases, either it may be glass fiber or it may be carbon fiber. Carbon fiber or glass fiber both have their own significant properties. So from that property, you can enhance by adding 28% of alumina particles, which is converted into nanoscale. So similar case also in flexural test also. So these graphs A and B, they are also showing that whenever we are adding alumina particle, it is the strength, either it may be flexural strength, tensile or modulus, all are improving. So this is a combined case. And wear test. So in wear test also it was there. Whenever you are using this alumina is 2%, 4%, 6% like that. And here glass fiber, carbon fiber and alumina, this is your weight percent and this is your dry specific wear rate. And this is your coefficient of friction. So as the pillar content is increasing, so we are getting this type of the dry wear test. So at 28% of alumina, it is the lowest. And here the coefficient of friction was maintained steadily, because here at whenever there is no particle, so the friction is more as we are adding the particles, because this alumina is abrasive material. So this is not reduced too much, whereas the carbon itself contain graphite, it can work like a lubrication. So at 10% it is following like that. So these are the cases. And this is a dry specific wear rate of glass fiber with alumina and glass fiber with 28% alumina. And this is carbon fiber with 28% alumina. And this is your coefficient of friction. Then micro hardness test. So here also same thing, let us understand mechanical properties. So here the load was maintained in this step and time was varied, 5 seconds, 25 seconds. So Becker hardness test, and in x-axis it's a weight percent of alumina. So up to 2% it is linear, and thereafter it is changing its slope. That means the agglomeration of nanoparticle is creating some loose, is reducing the strength of the matrix. So due to that, it is becoming straight. So up to 28%, it steadily it is increasing. Then fractographic test we have saw here. So whenever you are using, this is our pure epoxy, it is complete brittle failure. So after that, whenever you are keep on adding these alumina particles, so this fiber breakage, fiber pull out, ice, and this type of crack marks are showing that the property of our, whenever you are adding here, you see this at 28%, this is fiber, and perfectly it is bonded here. So like that, because the interfacial strength was increased, so due to that, it is getting more strength. So if you will see here, it is another microscope analysis. So in the microscope analysis, you will see how the fracture patterns are flowing. So these fracture patterns are proving that the strength of the matrix was improved. I think one broken fiber here, you see here. So at this case, you see the fiber is center one and the matrix still it is intact. So it was broken in the matrix side, it was tried, but it was not delaminated, it's not left this one. So that means the proper bonding is also happening whenever you are applying, adding some 28% of alumina. So time is already over. So just I will conclude here in voltage breakdown test. So this is type of failure is like a river flow pattern. So here also at 28% we are getting extraordinary proper enhancement in voltage breakdown test. So here in conclusion, what I can say that here with the addition of 28% and 5% of alumina particle, the breakdown time increased by 28%, it is 272% and 260%. So that is also one very big achievement. Then net gain of 155% in breakdown strength was observed in case of 5% The breakdown strength dropped to 88% due to the incorporation of 10% of alumina, and tensile strength also improved. The compressive strength was increased by 90% when 28% of alumina was used, and at 15% of alumina addition, the strength of the composite was dropped by 23. Naturally, it is expected because of the agglomeration. So in almost all the cases, whenever you are adding either it may be tensile or compressor flexural, so in impact also 84% was achieved and 28% was used. whereas that 35% enhancement was achieved and 3% of particles was added. So like this in short, in everywhere, whenever you are adding this particle, the strength was increased. So thank you. So I think I have taken a little more time.
Thank you, sir. So dear participant, session is open for the questions. I would like to request you please take opportunity and discuss with sir. You can unmute your mic and then ask question.
Good afternoon, sir.
Good afternoon.
What about the fatigue properties of this?
Sir, whenever you are discussing about the particulate reinforced polymer composites, in this case, we are not going for the fatigue test. So fatigue test, you can go for the fibers like unidirectional fiber. Definitely, it is 100%. I believe that whenever we are doing the fatigue test, which is very much useful test for unidirectional, bidirectional fiber, what property enhancement we are achieving by any other method, this method will give you the 100% better result. So this is, you can, sir, consider as a gap to do the test and publish this paper in this fatigue test. Definitely.
So that means this particulate composite will not be used for structural applications.
Sir, particulate composites are a base material. Whenever you are going for any structural elements or a component, we are using one matrix. Without matrix, we cannot make one three-dimensional set. So here I have given all the ideas about that matrix development. So after you are developing this matrix, you can use as a bidirectional. You can take bidirectional fiber and use the same matrix material, whatever was I have proposed by taking 28%, and use this one. You will get extraordinary results.
Understand.
नहीं आया sir. Okay. Next question. Monty sir, you can check the chat box. Mr. G. Kirubakaran want some clear the doubt. So, Mr. Kirubakaran, are you there?
Yes, sir. Yes, sir.
Yeah. Could you please ask question from sir?
Yes, sir. Thank you, sir. Good afternoon, sir.
Good afternoon.
In 3D printing, for the filaments, thermoplastic type only available, otherwise thermosetting like epoxy also available in a filament form, sir. Because
yes, sir. Yes, sir. Sir, in 3D printing, the main process is that it should be cure faster with the environmental support or a laser light like that. So if it will cure faster, sir, it is a very, this is a very next level of research. If you can make a light or make a environment, because we are talking about matrix, 3D printing also require a matrix. So it is taking a thermoplastic material, thermoset also nowadays is coming. So it will make the curing process, because it is making a layer and a layer like the nozzle it is doing. It will create a environment where you will get faster curing, because in here, whenever you are mixing the resin with the hardener, it takes near about 20 minutes. So it is a longer time to cure. So if you will reduce by innovative method that curing time and using this type of method, by using this type of particles, then it will be another advance and new search in this field. Because directly you cannot use epoxy, because it is taking some little more time to cure. It requires some chemical, some another technology to reduce this curing time.
Sir, one more question. Doubts are not. Sir.
Yes, yes, I am unable. Yes.
Sir, for composite laminates, they are using ASTM 3039 is correct, sir. But for 3D printing, in some journals, they are using 3039. In some journals, they are using D638, sir. Kindly give clear idea about this area, sir, because I showed your tensile and flexural specimens.
Actually, this ASTM standard, what they are following, maybe based on the some other factors. Actually, in this area, in this, I have not explored.
Okay, thank you, sir. Thank you, sir.
Thank you, thank you.
Is there any further questions?
The basic question, sir. Difference between tensile strength and tensile modulus, sir.
Sir, strength means energy required to break the specimen. Before breaking the specimen, how much energy it is observing. Whereas tensile modulus is a property in the elastic region. So that whenever we are not going for modulus test, we are not going for complete breaking. So this is the test which is giving the information in the elastic region. Wherever we are going for a tensile test, that means complete breaking. Once it will break means before fracture, how much total energy it was observing, that is called. But in our majority of our design requirement, we are working in a region where it should not go for distinguished plastic deformation. So we have to go below to our yield point. So in this case, the modulus is increasing, means it is absorbing more number of energy with a lesser deformation.
Okay. So due to lack of time, we cannot take more questions. If you have any other question, you can email to Dr. Akash. So I thank Dr. Akash for giving insights about using micron size alumina converted into nano size alumina. We can say that in situ nanoparticle dispersion which Dr. Akash achieved. So I thank you, sir.
Thank you, Pankaj, for giving this opportunity to share my thoughts and my research outcome. Thank you.
Sir, you can unshare the screen so that.
Yes. Thank you. I think Pankaj, it was on. I have on screen.
Okay, sir. Thank you. Thank you,
Pankaj. Thank you, all the participants. Thank you.
So, good afternoon, everyone. We have to start the next session, and I am conducting the next session. So, first of all, let me share my slides. Are you able to see my slides?
Yes, sir.
Okay. And my voice is clear now?
Yes.
Okay, fine. So I welcome everyone for this session. This session is on polymer blends, because after this session, Dr. Bose is going to talk, and he is also talking on blends. So what I thought is, let me cover some basics and give you a lot of idea about blend, and so that how this blends are helpful in 3D printing also, that we can briefly, I will highlight. So before starting going into blend, this definition you already know about the polymer. There are many repeating units, building blocks. So like this polyethylene, here you have a repeating unit of CH to CH2, polyvinyl chloride. Instead of one hydrogen, it is replaced by chlorine. And subsequently here it is a CH3, then it will be a polypropylene. So you say that carbon chain is a major backbone. So if you look at the structure, okay, so here there is a tetrahedral arrangement of the monomer. Now this is the repeating unit, okay, and not a crystalline one, okay. Now if you look at the addition polymerization, what you need to do is you are taking your monomer, there is an initiator, and that will create a free radical, and there is an addition of more and more monomer, and it will result in a bigger chain. And of course, there is a termination by disproportionation or the combination. Now, what are the polymers which are synthesized with the help of this addition polymer? So here you can see a whole range of polymers, from polyethylene to polypropylene, polystyrene, polyacrylonitrile, etc., etc. Now, another thing is condensation polymerization, where you are taking two chemical unit. This two chemical unit is reacting and forming the water as a byproduct, and here you are getting a one monomeric unit of nylon 6,6, okay, and then this reaction will continue. Okay, so this is the condensation polymerization. And yes, I think I have not taken another slide, but nylon 6 is one of the example of the condensation polymerization. Now, what is important in polymer is the chain length. What is the molecular weight? Maybe the number, how many number of monomers are there, number average molecular weight, or weight average molecular weight. In this case, when you polymerize any polymer, the chain lengths may not be same. There is a distribution of molecular weight. Okay, so that one of the aspects you need to keep in mind. So suppose you wanted to process your composite material or any polymeric material, okay, what is the influence of this molecular weight on mechanical properties? Now, if you wanted to process polymer with the help of twin screw extruder, now the molecular weight you need to choose is a lower molecule, not lower, but medium molecular weight, more than 10,000 or 20,000 weight average or number average. Okay. While for compression molding purpose, generally you are choosing the higher molecular weight material. Say for example, ultra high molecular weight polyethylene. Okay, as the name itself suggests, high molecular weight for implant which we are making. Okay, why? Because it is giving a very good mechanical properties. Okay, but if you start increasing the more and more molecular weight, processing become difficult. Like injection molding, you can't make it. Okay, now that is the drawback. That is the reason molecular weight has to be lowered. Now that in 3D printing, there is an opportunity for polymer chemists. They can make a higher molecular weight of polymer, and in a powder form, if they make, then yes, there are opportunities. Okay, but that has to be done by the chemist and make the powder available, so that engineers can print and then test the mechanical properties and other properties as per the product requirements. Okay, but that is a chemical basis challenge. So if you see nylon, polypropylene, all these polymers are semi-crystalline in nature. Okay, if you see metal, it is a crystalline material. But if you see polymer structure, see this is the one chain, this is the another chain. Okay, now these number of chains, it is forming a unit cell here, and this unit cell is forming a long range order. So this is your crystalline region. While irregular arrangement of the chain or random arrangement of chain, here you have amorphous region. So in case of your polymer, you have crystalline region and amorphous region. And with certain characterization technique, you can easily calculate the crystallinity. One of the characterization technique is differential scanning calorimetry. Now we can contour a blending. As I said, for twin screw extrusion and injection molding, you cannot take a very high molecular weight polymer. Okay. So in the market, if you go and purchase the polymer, they will ask which grade of polymer you wanted. Okay, low molecular weight, high molecular weight or very high molecular weight, or injection molding grade or compression molding grade. That way also the polymers are available. So you just take the polymer with a lower melt flow rate. Oh, sorry, a polymer with a little higher melt flow rate. Okay, because here your granules has to be extruded inside the mixture. Okay, now this is the twin screw extruder, and when you see the twin screw extruder, you are mixing two different polymers in order to prepare a blend. Now what is blend? Blend is nothing but a mixing of two polymers, okay, with the help of an extruder. We have to give certain energy so that the mixing takes place. Now why people wanted to go ahead with the blending? A simple reason is, take a polymer, polypropylene, a very good polymer. But the problem with polypropylene is, it is having a good tensile properties, but very poor impact properties. But while if you take acrylonitrile butadiene styrene, that is another block copolymer, it is having a good impact properties. Okay, so if you mix the combination of these two, what you can get is, you can get good tensile properties as well as good impact properties. Okay, now how the mixing is taking place inside this twin screw extruder. Now when these two granules are added, so what will happen? This region, in this region only the mixing of these two granules takes place, physical mixing, there is no melting. But in this case, in this zone to this zone, there is a melting of polymer. And here in this zone, you have a two-phase mixing. And finally, what you will find out from this end, the extruded strand is coming out. Okay. So we have seen in twin screw extruder, there are zones. Okay. In zone, A and B pellets are mixed. Okay. Here the melting takes place. So this is one of the polymer, say dark area B polymer. So what happened when the melting started? See, this B polymer started stretching because of application of shear forces. See here, there are gaps, okay, and there is application of shear forces. Now this will elongate, okay. Now what will happen depending upon the fraction? okay, depending upon say volume fraction. Okay, there is a formation of two different kinds of morphology. There is a co-continuous morphology and there is a dispersed morphology. Okay, now what is this dispersed morphology means? Say for example, polypropylene and acrylonitrile butadiene styrene blend, if the composition, okay, say composition of acrylonitrile butadiene styrene is 20%, then there is a formation of droplet like this. If composition is 50-50, then there are the domains of ABS, which you can see it here. So co-continuous morphology will be formed. Okay, so we can see that by mixing two polymers, there are formation of two types of morphology. One is matrix droplet morphology and another one is a co-continuous morphology. Okay, now why people wanted blends? Okay, now if you see the companies which are selling polymers, say for example SABIC is the one of the company who is selling polymer. Now SABIC, what if you go to their product library, they will say that we are selling BC-ABS blend, okay, one of their products in the form of granules. So the blend, PC-ABS blend, is commercially available in the form of granules. Okay, now why this PC-ABS blend is available commercially? Because it is giving a very high impact properties. Okay, and in case of automobile industry, in automotive interiors, you will see many products which is made from PC-ABS blends. Okay, so the blends are very important, and the companies are selling these blend granules. Okay, so you can imagine what kind of market it is having, especially in case of engineering application high end, not just buckets and your mug, okay, or a simple packaging material of polymers. Okay, I'm just talking about the high end application where the profit margins are high. So there the blends are used. Okay, so blends are very important. So what we thought is, let us prepare the blend nanocomposite, and we have chosen halosite nanotubes, okay, which exhibit kaolin chemistry. Okay, so halosite, what is halosite? Halosite is nothing but your aluminosilicate. Okay, now if you remember my morning presentation, a multi-wall carbon nanotube is a high van der Waals forces, but halosite nanotubes, there is a weak secondary interactions. So this can easily dispersed in polymer matrix. Okay, so for this simple reason, we have chosen the halosite nanotubes. If you compare, this is a non-conducting in nature, and while the carbon nanotubes are conducting in nature. So that is the reason carbon nanotubes are again attractive for multiple applications. So as I discussed earlier, polypropylene, good mechanical properties, low cost, excellent chemical resistance, a very beautiful material, but the low impact strength. Okay, now this can be improved by addition of acrylonitrile butadiene styrene. Okay, so what we did is, we have taken a polypropylene 80 weight percentage and ABS 20 weight percentage, and we prepared the blend with the help of this twin screw extruder. This is counter rotating type twin screw extruder. These are the operating conditions. So this is the hopper from which we have fed the polypropylene and ABS granules. And this is the barrel in which the polymer is fed, it gets melted, and here is the nozzle from which the polymer strands are coming out, and these strands will be further chopped off. And behind you see there is a mini injection molding machine with the help of which we can prepare the tensile and impact specimens. Okay. Now the concentration of halloysite nanotube is 1, 3, and 5.8%. Okay. So initially we have characterized the halloysite nanotubes. So the as received halloysite nanotubes consist of this aluminum, silicon, and oxygen with the help of EDAX, and it is more than 20 nanometers in diameter. And then we have further taken the XRD, so it exhibits the halloysite nanotube is crystalline in nature. So once we mix this blend of PC and ABS, we wanted to see what kind of morphology is there. So as expected, this is the 80-20, 80% polypropylene and 20% acrylonitrile butadiene styrene. So morphology appear like this. Why here you are seeing the porosity? Because ABS, we have etched it out. Chemically, we are just removed it out so that you can see the here the droplets of ABS. But these droplets are not spherical droplets. Okay. But if you add halloysite nanotube, these droplets are refined, okay, because of the breakage. Okay, and you can see a droplet size decreases here, but here it is a little increase. Here it is a non-uniform distribution. Okay, as the halloysite nanotubes start increasing. So why there is a refinement? Because there is a spanning nanotubes lead to the breakage of dispersed phase. So one can say that in polypropylene ABS, the droplets are droplet size distribution, and the size of the droplets are bigger. By addition of halloysite nanotubes, the droplet size becomes smaller. So there is a refinement in morphology. So HNTs, halloysite nanotube, act as a compatibilizer. Okay. Now we have taken the X-ray diffraction. So a pure polypropylene is showing these peaks at this location, and this location, which is the alpha monoclinic form. And here at this location, it is a beta monoclinic form. Okay, which is important for impact. But in presence of HNDs, the beta content increases. Okay, so your halloysite nanotube act as a beta nucleating agent. Okay, so we have done the characterization with the help of differential scanning calorimetry, and from this melting endotherm, you can easily calculate the crystallinity. This crystalline exotherm is showing what is the crystallization temperature. Okay, crystallization temperature. Okay, the temperature at which your crystal structure formation. So this is the temperature. This is the temperature at which crystal structure formation start, and this is the temperature at which the crystal structure formation finish. This is the temperature at which 50% of the material get crystallized. Okay, so this crystallization temperature can be noted, and the crystallinity can be noted from this enthalpy melting endotherm, the area under this curve, okay, divided by area for 100% crystallinity. If you take that ratio and multiply by 100, you can easily calculate the crystallinity. Now here you see the crystallinity of polypropylene is 43%. While when you start adding the halloysite nanotube, the crystallinity remarkably increased. Okay, here it is at 1%, it is 51.4. Now why 51.4? The answer lies here. Because there is a huge a surface area of contact of ABS with polypropylene, as well as halloysite nanotubes act as a heterogeneous nucleating agent, and that's the reason more percentage of polymer get crystallized. Now this has resulted in increase in tensile properties at a small concentration, 1%, tensile strength and tensile modulus. So if you look at this is the first image, what you are finding out, there is a pull out of ABS droplets. Why? Because there is no interaction. Well, it's pretty simple. Okay. And we have done the tensile impact testing, and then because of good dispersion, impact strength also enhances. Here you can see the impact fracture mechanism. The ABS droplets will pull out because there is no interaction. Now, in order to improve this interaction, I will skip this slide. Okay. In order to improve this interaction, a compatibilizer need to be added. Okay. Now, what is mean by compatibilizer? Compatibilizer here we are using is polypropylene grafted maleic anhydride, and there is another polymer which is SCBS grafted maleic anhydride, styrene, ethylene, butadiene, styrene. Now, what is the rationale of using this compatibilizer? So any compatibilizer you see, it is having a low molecular weight. Okay. And it is added in a small concentration. Say here 5-8% it is added. Okay, both. Now, when you see this PP and ABS, what is the concentration here? 80-20. Ratio is 80-20. Okay. Now the PP and ABS as compared to this is having a high molecular weight. Now, when you mix this PP, ABS and this compatibilizer in twin screw extruder, now what will happen? You have a droplets of ABS and there is a PC matrix. So this low molecular weight polymer will be between this interface. What I'm saying will be at the interface. Okay. Now, because this low molecular weight material will be at interface, so what will happen? It will help in the stabilization of the morphology. That is the reason these polymer low molecular weight of functional groups are attached like maleic anhydride. It is referred as compatibilizer. Okay. So here if you see why these two compatibilizers, so here it is polypropylene. So like dissolve like. See here the one of the blend material is polymer. So compatibilizer must consist of polypropylene and there is a grafting of a small molecule that is maleic anhydride. Okay. Similarly, here styrene, ethylene, butadiene, styrene. Okay. Now here acrylonitrile, butadiene, styrene. So butadiene and styrene is there. Here also styrene and butadiene components are there. Okay. So this will interact with this ABS also. Okay. And I said earlier, PP and ABS at the interface, this SCBS will be there. Okay. So we can say what is the influence of this addition of two compatibilizer. So here you see a significant refinement in morphology as compared to earlier SEM. See, okay, if you see this previous SEM here, okay, the same magnification is same. Here it is a bigger droplets, but when you add a compatibilizer, the morphology is refined. There is a formation of smaller and smaller droplets. Why? The interaction between nitrile group of ABS and maleic anhydride group of compatibilizer. This is one reason. And this interaction lowers the interfacial tension. Okay. Now, what will happen? See, ABS, suppose if it is covered by PPGMA, because it is an interface. Okay. Now this is small droplets, and because of mixing during polymer processing, these small droplets cannot come together. Why? Because you have PP and you have PP, and again the PP matrix phase. So there is no chance that this droplet will be coalesce or combined together. So coalescence may not happen. And that is the reason here you have the formation of finer droplets. Okay, please understand. Inside the shear mixing, there is a without compatibilizer, there is a continuous development of finer droplets. These finer droplets combine together and it's make bigger droplets. Okay, fine. And then the morphology after injection molding, you may see a bigger droplets, but because of compatibilization, the combination or coalescence of droplets will not happen. Okay, and that is the reason you are observing this finer morphology. Fine, and that is the reason companies are selling the blend products. Okay, fine. Bigger companies are selling the blend products, blend granules, and then automobile manufacturer by using it, they are making components. So you can see this is the diameter of polypropylene ABS with compatibilizer. In presence of HNTs, the diameter further reduces, and we have calculated the interparticle distance with this Turner-Jones equations, and interparticle distance also changes. Okay, I will skip this slide because this is the beta nucleating agent forms. Okay, so when you see the DSC, what you have observed is, see here, with compatibilization, okay, the crystallinity is 39.7. Okay, but when you add HNTs, crystallinity increases because of heterogeneous nucleating effect of HNTs. Okay, so that is the role of HNTs. So what we have seen is a tensile property enhanced at 1 wet percentage. Here is at 1 wet percentage of tensile modulus. But earlier observation without compatibilization, we have seen the pull out of droplets. But in presence of compatibilization, because there is an interaction, the pull out of droplets are not happening. Okay, but instead of that, a breakage of droplets is happening. And that is the reason here, if you see the comparison, this is uncompatibilized. So compatibilized tensile strength as well as the impact strengths are very, very high. Okay, now why impact strength here is very high? Because if you see this image, there is a huge amount of smaller droplets and which are pulled out. Some are fully pulled out. Okay, so some are fully pulled out, but most of the droplets are intact. So it is absorbing more amount of energy, and that is the reason this impact strength is improved significantly in case of compatibilized blend in presence of halloysite nanotubes. As well as the thermal stability is also enhanced because this TG curves shift to the higher temperature. Okay, so just 1 minute. Okay, now till this point, what I did is I just talk about the role of your one of the filler halloysite nanotube and this compatibilization. How can we control the morphology, whether it is a matrix droplet morphology or it is a co-continuous droplet morphology? We can control with the help of compatibilizer, one, and second with the help of nanotubes or fillers. Okay, now why I'm covering this part? See, because yesterday Professor Ravi Kumar, he suggested that the wires or FDM, we do not have too much control, or you have a simple choice of using ABS as a material or polylactic as a material. Okay, but the composite actually filaments even are not available easily, and if it is available, no one is giving guarantee. This is for just marketing purpose. They are just introducing the market. Okay, but the reliable blend or reliable filament, okay, this filament you should use for this particular application. Okay, you have 3D printer. Now this 3D printer, you need to make a product. Okay, so you don't have SLS machine, that is okay, fine. But if you have a control over the morphology and your 3D printer processing parameter you control, and then if you're able to achieve a good properties or the properties which is suitable to meet the design requirement of a particular component in automobile industry, that will be the achievement. Okay, so that in with that context, I have taken this topic for this session. Okay, now compatibilizer and nanofiller need to be added, but the nanofillers you also need to modify. Okay, so what we did is we have used branch polyethylene imide to modify the haloside nanotubes. Okay, and again we use this modified haloside nanotube in PP-ABS blend in presence of the two compatibilizer. Okay, now what we did is we have done a processing. Okay, PI modified haloside nanotube literature was available. We follow the same protocol, and with that protocol, what we have observed is here you have the interlayer H2O haloside nanotubes, and here there is an absence. So there is some interaction in between your HNTs and PEI. Okay, I think I have not taken the TM image. So the TM image, what we have got is there is a coating of polyethylene imine over HNTs. The second reason why using polyethylene imine, it is having an amine group. The amine group is reacting with this maleic anhydride. Okay, so that is the reason we have modified HNTs with polyethylene imine. And again, we have started characterizing the morphology. We are getting a pretty refined morphology. There is no much change. Okay, we have calculated a diameter, we have calculated the interparticle distance. It seems pretty fine. Okay, now we wanted to understand where this haloside nanotube is located, whether it is located in polypropylene phase or it is located in ABS phase. Okay, so what we did is we have taken the strand of the PP-ABS blend and that dissolved with xylene. So only the PP will be dissolved here. And then again, we take the same strand, okay, of PP-ABS blend and dissolved in a tetrahydrofuran. So here what we are observing, we are observing a clear solution. But here in PP case, because of the presence of HNTs, the solutions look clear. So what does it suggest? It suggests that the HNTs is dissolved in PP phase. Okay, and because of which you will see there is a formation of alpha and beta phase. That is the reason here the crystallinity which is achieved with the help of DSC. Here you are seeing it is having a good increase in crystallinity. Now what we did is we try and compare the three composition. This is your PP-ABS blend in presence of compatibilizer. B is PP-ABS blend in presence of compatibilizer with haloside nanotube, 3 weight percentage. So this is the SEM image. Okay. Now here, if you see here, it is little coarser. Here the morphology is little finer. And in presence of modified haloside nanotube, a finer morphology is achieved. See here, the finer morphology is achieved. Okay. Now, when you compare the crystallinity, okay, because of chemical reaction in between amine group and maleic anhydride group, what you will find out that the haloside nanotubes are not exposed to PP in a larger fraction. So there is a small decrease in crystallinity here. Okay. But it won't affect the tensile properties. So tensile property is in case of modified haloside nanotubes, here it is more. Okay, significantly enhanced in case of 3 weight percentage haloside nanotubes. Okay, very significantly enhanced. So here you see in case of HNTs, modified HNTs, here if you compare the fibrils, see here, the fibrils are bigger. But here the fibrils are finer. Okay, and finer fibrils are able to bear a larger amount of load, and that is the reason the tensile properties enhances, tensile modulus as well as the tensile strength. In addition, the impact strength also enhances significantly. See here the impact strength values, kilojoule per meter square. It is just roughly around 114. It increased to around 190. Significant improvement in the impact properties. Okay, so we can say that the haloside nanotube modification is influencing the crystallization as well as the mechanical properties behavior. Thank you for patiently listening to my presentation. Your questions, please. You can unmute your mic and then ask questions. Exit screen. Okay. Any questions from audience? Krishna. Okay. So you are interested, I will just give one suggestion. You are interested in 3D printing and polymer filament you wanted to use. So with this kind of research, how to make a blend filament and then how this blend filament to be used in your own 3D printer. Okay, so what you need to do is you pick up a blend from the literature which is used in automobile industry. You mix that blend with compatibilizer, you check the literature, select the filler material properly, and try to find out a collaborator who is having a twin screw extruder who can extrude. Even some companies, they can help to extrude small batch. Once you take a granule, you take that granule to a company who are making 3D printing filaments. So they will draw a 3D printing filaments for you. Okay, fine. Once these 3D printing filaments are drawn, then you can use your own 3D printing machine and then print various shapes, maybe dog bone shapes, impact specimens, and the product which you wanted to implement that product. Start printing it and then see how it is performing as compared to the current product. Currently, there is some polymer which they are using. Okay, fine. And in this way, if you proceed, there is a chance of implementing your solution in the industry as well as the publications. I think this point may be of interest to you. If any other points, question you wanted to ask, feel free to ask me. Okay, if there are no questions, then we can wind up this session, and we can meet once the Professor Surya Sarthi Bose joins. Okay, thank you for joining. We can meet in 10 minutes. Good evening, Dr. Surya Sarthi Bose. Dr. Bose, can you hear me?
Yes, Pankaj.
Okay. So we can start at 3 o'clock.
Sure.
What I did was just in 2:45 presentation.
Right.
I discussed something about little bit about polymers.
Okay.
And I discussed little bit about the blends also.
Okay.
So I have discussed the what kind of morphologies are there.
Correct.
So as a case study, I have put matrix droplet morphology.
Okay.
And what is mean by compatibilization and how compatibilization can control the morphology and its influence on mechanical properties. And a Praveen case study I have taken, so halosite nanotubes and its modification,
right.
And how it is influenced the properties and how can we tailor the properties.
Okay.
That part I have covered so that it is easy for you to deal in 3 o'clock.
Sure. I can then go a little fast on those topics.
Yes, sir. So then, sir, can you check? You can share your screen.
Okay, let me try. Are you able to see?
Yes. You can make just full screen.
Just see if it's okay.
Yes, it is okay. Now we can start at 3 o'clock, sir. I will introduce you.
Okay.
And after that, I will hand over the session to you.
Sure. I will then stop sharing for a while. You have few corrections to be made. Okay, so 3 o'clock.
No problem, sir.
3 o'clock I'll join again. Yeah.
Okay.
Bye.
So Dr. Bose, can we start? Okay, sir. Okay, sir. So first
Can
of all,
you-
I will introduce you, and then I will hand over the session.
Sure.
So good afternoon, everyone. I once again welcome every one of you for this session. This session is on polymer blends and their composites for EMI shielding application. And this session will be taken by Dr. Surya Sarthi Bose, Associated Professor in Indian Institute of Science. And Dr. Bose was my senior during PhD days. We worked in the same lab, and those days he published even 10 or more than 10 number of papers from his PhD thesis. And thereafter, he has a postdoctoral stint in Catholic University, Leuven, and then thereafter he joined Indian Institute of Science. And in different areas he worked, multi-scale composites, then EMI shielding is his major focus. And I think water filtration application blends nanocomposites for water filtration and many more areas, in the biomedical materials he worked. So I hope his talk will be very informative for you to get more insight. So with this few words, I hand over the session to Dr. Bose.
Okay, thank you, Pankaj. Am I audible and are my slides visible?
Yes, sir. Audible and visible. No issues.
Okay, perfect. So good afternoon, everybody. At the outset, let me thank Pankaj for having me for this webinar. So there has been long association with both Pankaj and VIT. As Pankaj said that we worked in the same lab at IIT Bombay, 100% Bhattacharya back then. And we enjoyed working together at IIT Bombay, and then of course, as life decides, so we separated out and we moved on in different directions. And with VIT, I have long association. I served in doctoral committee, and I think one more doctoral committee meeting is soon coming up. So that's a short introduction with introduction. I mean, my association with Pankaj and VIT. So let me come back to my presentation for this afternoon. So I'm going to talk on polymer blends and their composites for EMI shielding. So my name is Shurjo, and I'm a faculty at IISc Bangalore. And our group primarily focuses on designing new and unique blends and composites for various applications. One such application is EMI shielding. So we are more interested in making materials that can block or rather absorb the incoming electromagnetic radiations. And we are mostly interested in the microwave frequencies because that's where most of the operating frequencies are, from mobile phones all the way up to radars. And in this process, we have actually created a library of materials that can absorb electromagnetic radiations when they fall on them by different mechanisms, which we will learn this afternoon. Okay, so right. So I'm now on slide number 2. So this is a brief overview of what I'm going to talk this afternoon. So I will introduce blends, which Pankaj has already done it. So I'll move a little fast on those topics. I will talk on the need for blending and the methods. And then we'll see some typical examples that why do we need to blend polymers. And most importantly, we'll see what are the different morphologies that evolve and which particular morphologies are of interest to us, especially concerning in designing conducting blends. And then I'll introduce you to electromagnetic interference, EMI as we call it, why there is a need to design those kind of materials that can block electromagnetic radiations, and what are the mechanisms when you actually design a material. You need to know what is the operating frequency, what are its requirement. We'll go various case studies from my lab and also some state-of-art literature on blends with blends that are used for electromagnetic interference shielding. And then we will, in the next part of the talk, I will talk mostly on the hybrid fillers, because you will learn from the part 1 that not a single filler can actually do all the job. So we need some hybrid materials to block both electrical and magnetic fields of the electromagnetic radiation. So therefore, you need a material that are conducting or dielectric or to some extent magnetic and so on. So then we will again see in the second part of the lecture where blend systems with hybrid fillers. And again, we will see that why certain morphologies are very important than the other. So probably you might have heard from Pankaj about polymer blends. So basically when you mix two polymers or two copolymers, you create a polymer blend. But then when you just mix two polymers, most often you will see that they are highly immiscible and chemically incompatible. That's because their chemical architecture is very different, their physical properties are different, there are no reactivity between them and so on. Although certain polymer blends do react and certain polymer blends are miscible because they share some specific interactions between the two components. But most often you get a highly immiscible system where there is a sharp interface is developed because of blending. So as you can see that if you are mixing two component 1 and 2, the red ones are the dispersed phase and the blue one is the continuous matrix. So we call these as matrix droplet type of morphology. Now, when I say that certain blends do share some specific interactions between them, so these are called partially miscible blend. They're not completely miscible at all length scales. So therefore, they are only partially miscible blends. And of course, the thermodynamic criterion is the delta G, which is free energy of mixing, should be less than 0. And the second derivative of the enthalpy is greater than 0. So these are some of the requirements for a blend to be miscible. And besides from thermodynamic criterion, blends are also miscible. If your second component is very, very small, for example, if the second component is a minor fraction, let's say 1% or 2%, they can be miscible at certain length scales. So, for example, if you run a DSC on these type of blends, you might see a single TG, which is glass transition temperature, but that necessarily doesn't mean that the blends are miscible. It is just that the second phase is in minor fraction, which DSC is not able to pick up the signals. So therefore, TG, that is glass transition temperature, is sort of insensitive to thermodynamic miscibility. So you have to be a little careful when you call a blend miscible or partially miscible. So you need to do multiple characterization to make sure that the blends are miscible down to molecular length scale. And as I said, if you are mixing two components 1 and 2, most often you will see that they are immiscible, which means the free energy of mixing is greater than 0. So there is very poor interaction between the two phases, and because of this poor miscibility, they form a sharp interface. Okay. Pankaj, can you see my cursor?
I can see, no issues.
Okay, perfect. So when we mix two components 1 and 2, you actually have a very sharp interface. So the sharp interface is relatively weak, and therefore they have poor physico-mechanical properties. And that's the reason why we prefer some amount of specific interactions between the components so that a more finer morphology is generated rather than a coarse or a coarsened structure in the case of immiscible systems. Now let's go back a little bit and understand what are the reasons for blending. Of course, certain polymers come under engineering plastics and they are relatively expensive than the commodity ones, which are cheaper. So one reason could be that you can blend a low-cost polymer with a high-cost engineering plastic to cut down the cost. But cutting down the cost also comes with a surprise of poor interface. So therefore, you need to also take care of the interface. You might develop a broad range of property by mixing two polymers A and B. And the other reason for blending would be that you can adjust the composition at any point of time to suit the customer, and thereby you reduce the scrap. So these are some of the prominent reasons for blending. Let's see what are the methods of blending. Mechanical mixing is the cheapest of all, but there are also casting from solution using a co-solvent, latex blending. You can also mix to fine powders, or you can create an interpenetrating network where you can start off from monomer and try to polymerize inside a polymer, and thereby you get IPN, which is interpenetrating network. So these are some of the methods of blending, and these are some of the reasons. So pictorially, if I have to show you, so this is solution blending, which is the easiest of all. You do not need any heavy infrastructure to do this. You take a polymer, you try to dissolve it in a suitable solvent, preferably good. When we call it good solvent, which means a theta solvent, where this polymer, the random coils, these polymers actually open up because they can swell in a good solvent and they can mix properly, and then you cast it in a Petri dish, try to evaporate the solvent and take out the film. So that's the best way of making a blend. But of course, as you can see that you need to dissolve in a solvent, and most often you will not find a green solvent, so that these are harmful organic solvents, and then you need to evaporate the solvent. That's again a challenge, and then finally you get a film. So from step 1 to this step, it might take about 3 to 4 days. So the turnaround time is quite high. Whereas the industrially relevant techniques are melt compounding or melt blending. So you can use an extruder. You can dump your component 1 and 2, mix it thoroughly under high shear and temperature, and then you can extrude them out, and then you can either mold them or you can go with compression molding and make a sheet and so on. So here the turnaround time is quite quick. So in a single day you can make many formulations. So melt blending is always a preferred technique over solution blending. Of course, if you are working on a new system, it is always better to start off with the solution blending thoroughly characterized, because the amount of material that is required here is less as compared to melt blending. So now when you are mixing two components 1 and 2, you need to understand the properties of each ingredients, like why are we mixing these two. So probably some of the advantages of one can be used to cover up the disadvantages of the other one. So their content is again very important, because based on their content, you get a range of microstructures. So I have underlined this third point, which is morphology and microstructure, because the whole lecture of this afternoon is based on the different morphologies that evolve when you mix two polymers A and B. So on the top, you see a few uncommon morphologies. I will put it this way. The most common ones are the matrix droplet. That means if one is major fraction and the other one is in minor fraction, the minor fraction is sort of dispersed in major fraction. For example, it looks something like the first one. And here I have encircled one morphology, a class of morphology, which is called co-continuous, which means where both the phases are sort of continuous. So that means when you're trying to mix component 1 and 2 in similar proportions, you see that both the phases are continuous, and which is of high interest to us, because we would like to explore this morphology further for developing some blend composites and use it for electromagnetic shielding. The other morphologies that you see, like double emulsions, laminar, ordered phases, and fibrillar, are very, very special, and you need certain parameter changes in order to get to these morphologies, and they are only for very special applications. So let's move on with these two type of morphology, rather one which is co-continuous, and see how they can be used for various applications. So these are some of the additional advantages of blending. So one is recyclability, because we know that you don't have to store different grades, but by changing the composition, now we know that you get different morphologies. You can actually, you don't have to store these grades, but you can make a quick formulation changes whenever you get an order. So therefore, the number of grades that need to be manufactured and stored, you can reduce that. Quick formulation changes you can make, and these can be recycled because they are all thermoplastic blends. Okay, so these were some of the advantages, the reason, and the methods of blending. And we also learned about the different microstructures that are important. So let's focus more on the co-continuous morphology and try and understand that why this particular morphology is very, very attractive. So if you look at this picture here, this is an SEM scanning electron microscopic image of a blend from where one of the phase has been etched out by using a suitable solvent. So the remaining pits that you see is the other phase that has been etched out with a solvent. And I have, to guide the eye, I have drawn this yellow line here, which shows that this, if you follow this yellow line, you can actually see that the other phase that is not etched out is sort of continuous through and through. Okay? So which means that if I have to fill with some nanoparticles into the system, and all my particles actually are in this yellow line, my entire blend becomes conducting, if I'm using a conducting filler, or it gets some functional properties depending on the filler material that I'm going to add. So therefore, co-continuous morphologies are very interesting, and people soon realize that we can fill in one of the phase with conducting polymers like polyaniline, pyrrole, p-dot, polythiophene, and so on. So if I fill conducting polymer in one of the component, I can actually make the entire blend conducting. So these conducting polymers that I just mentioned are difficult to process. So they don't form film easily, they don't go in a solvent easily, but they can be blended with a thermoplastic blend. And if you are lucky, and if you can put all these conducting polymers in one of the phases, the entire system becomes conducting. And therefore, you actually get conductivity at much lower concentration of these conducting polymers. Similarly, if you are using conducting fillers like graphene or carbon nanotubes, you can start filling them in one of the phases, and the whole system becomes conducting. And that is the reason why co-continuous morphologies are very, very important and very interesting for this particular field. So that's a short overview of polymer blends, the different morphologies that generate, and a particular morphology that interests us. Now let's move on to electromagnetic interference shielding. So let me tell you what it is all about. So for example, we know that microwaves interact with materials based on their characteristic. So for example, if you have some dipoles in the system, the microwave can interact with these dipoles, and then they either get reflected, or they get absorbed, or they just transmit through and through if there are no materials that interact with the microwave. So for example, let's learn from a simple thing of a microwave oven. We all have seen a microwave oven in the kitchen. So if you carefully look at the door of the microwave oven, there is a glass, and on the glass you see some checkered pattern. Okay, so why do we need that pattern? Let's say, why not only glass? So we know that glass doesn't interact with microwave at all. So what that means is, if the door was only a pure glass, the microwave radiation would just come out of the system and it would interfere with something else. Okay? And in order to avoid that, we have this checkered thing on the glass, and this checkered thing is carbon fibers. And if you carefully look at each square is less than a millimeter length, because microwaves are also called millimeter waves, because they operate at high frequency of about 2.45 gigahertz. So therefore, all these microwave radiation that is generated by microwave should be reflected back inside the oven, and they shouldn't come out of the oven. That's the reason it's not a plain glass, but there is a sticker which is nothing but carbon fiber, nicely printed on the glass. So each carbon fiber is a reflector, so they will reflect back all the incoming electromagnetic radiation, which is microwave in this case, into the system back. And that is how your food is cooked much faster, because microwave interact with water molecules because they have dipole and they can vibrate, and this vibration can produce some heat, and this heat is enough to cook your food. So this hints at something, that if microwave radiation fall on your skin, so they may not burn, but they might cook your tissue up. Okay, so there are a lot of studies which indicate that if you are exposed to microwave for a very long time, your tissues get heated up. Now, what does it further do is something which is debatable, but all we know is exposure to microwave is not very, very safe for us for a very long time. So now you can argue that, okay, we all talk on mobile phone for hours together. So yes, as I said, that the after effects of exposure to microwave is still debatable. So we do not really know that how much exposure and for how long the exposure could actually create some problem for human body. So let's leave that part. What we need to do now is, let's leave the human body apart. So let's focus more on the equipments. So if there is an equipment which has precise electronics, they may get interference from the neighboring electronics, which actually produces electromagnetic signals or radiations at a different frequency. So what would happen is, if you are engaged on your landline phone, and if your cell phone beeps, you hear some interference on your landline because they start cross-talking with each other. And therefore, we need to shield these electromagnetic radiations, and therefore you need to design a material that can absorb or reflect electromagnetic signal at a particular frequency. And therefore, these shields that we design are called electromagnetic interference shields. So if you consider that this block is a shield, and you consider this as incident electromagnetic wave, so had this been a pure metal, so we know that the electromagnetic radiation do not interact with metals, rather from the skin itself they are reflected, okay, because they produce an equal and opposite electric current inside the system, which doesn't allow the incoming electromagnetic radiation to penetrate through the shield, and therefore they are reflected back. Now imagine that this shield has materials that can interact with the incoming microwaves, for example. So they can start interacting with the microwave. Part of it might be absorbed, part of it might be reflected back and forth inside the shield. And what you finally would see is that they are attenuated. And had this been glass, for example, which is non-metal, not interacting with microwave, then all the incoming electromagnetic signal would just pass through. So glass is a very poor material for this particular application. So on the right hand side, you actually see a particular piece of equipment which is called vector network analyzer. This particular equipment tells us the return loss, it tells us the intensity and the power of the incoming electromagnetic radiation. It also tells us the power of the output or outgoing electromagnetic interference. And from some algorithm, it gives you understanding about 4 parameters, which are called scattering parameters. And from these 4 scattering parameters, one can arrive at the shielding effectiveness, which is usually measured in dB. Just like the sound waves which are measured in decibels, this is also measured in decibels. So now, once you know the shielding effectiveness in dB, we know it's a loss. So we actually use a negative symbol, which indicates it's a loss or attenuation. Now, anything that crosses minus 20 dB is commercially relevant. That means it can block about 99.99% of electromagnetic radiation. When we say block, it could be reflection or it could be absorption or a combination of these two, but not transmission. So we know that metals are good conductor of electricity and hence they are good reflectors. So if you want to protect a precise electronic device, all that you need to do is you just wrap it up in an aluminum foil and you can actually shield it. But we know that metals also have certain issues and challenges, like they can corrode over a period of time, fabrication itself is expensive, and so on. And that's where people started looking at alternative materials, and alternative to metals for certain applications are plastics, where they offer lightweight, flexible in design changes, flexibility in processing and making composites and so on. So therefore, polymer composites very soon became an attractive material for electromagnetic interference shielding. And that's where our interest also lies in. So as I said, that electromagnetic pollution is everywhere. Sometimes you will see some reports calling it pollution. Sometimes you will hear it as interference. They're all the same. And why should we worry about? So for example, this cartoon is taken from Google Images. So you can see a person surrounded by a variety of electromagnetic radiations that could come from the DC motor, that could come from the transmission lines, from cell phone towers, from laptops, desktops. So wherever you have some electronics embedded in it or high voltage transmission lines, all these actually generate electromagnetic radiations. And we are actually surrounded by various electromagnetic radiations. More than us, the modern days aircrafts are more vulnerable to this kind of pollution or attack, because as you can see that these days most of the aircrafts are all automated, which means it is talking to the satellite, it is talking to the nearby aircraft, it is talking to the ATC, it is also talking to the radar and so on. And it is also talking with the runway, because many of them are equipped with the instrument landing system, ILS, and therefore modern day aircraft is surrounded by various electromagnetic signals or radiations. So now if you can imagine what happens if it starts cross-talking with each other, then it could be a mess, because none of the readings would be then correct. So however, the modern day aircrafts are all equipped with proper electromagnetic shielding, and that's the reason they can talk with different entities at different frequencies without any interference with each other. And that's how it could land safely. But they are still in a vulnerable position, because you never know which material would fail, and then there could be disaster. This is a simple example that if you have a woofer system and you bring a mobile phone near the woofer system, you will see a lot of interference between these two. So that's because if both are connected with Bluetooth or Wi-Fi, they start interacting with each other, and there could be a crosstalk and messy interference with each other. So which also means that the cell phones are not properly shielded, or the electronics in the sound system is not properly shielded, and they started interacting with each other and so on. So this is the state-of-the-art literature of different research papers that are published in the recent times. And as you can see that if you look at the last decade, from 16 all the way up to 20, the number of papers have gone up significantly, especially in this field, and more research groups are working towards materials that can block electromagnetic radiation. And what we have tried to do is try to pull out or give you even more details like polymer composites using foam, polymer composites using multi-layered structures, and so on. So if you look at that breakup also, you will feel that more and more research is focused towards foams and porous structures rather than sandwich or multi-layered structures. More and more research is focusing on foams because foams are very good electromagnetic interference material, shielding material, because foam have open cell and there is air in it. Air is a very good dielectric material, and that is how your electromagnetic signals are sort of trapped inside the foam, and it can protect your precise electronic system. So now let's try to understand that if you are designing a shield material, what all you need to keep in mind. So as I said, that metals are good conductors of electricity, and metals are good reflectors. So the surface charge that is developed on the metal produces an electric current whenever electromagnetic radiation falls on it. And this electric current that is developed on the surface doesn't allow the electromagnetic radiation to penetrate through, and therefore all of it is reflected from the surface. We call it surface reflector. And if the material has dipoles and if the material can interact with incoming electromagnetic signal, then it starts absorbing or reflecting inside the shield, and therefore it attenuates all the incoming electromagnetic radiation, and it hardly transmits any wave. So multiple reflection is something which people have now realized, that if you have a polymer composite with different kinds of fillers in it, for example, polymer composite with carbon nanotubes, so each carbon nanotube might be a good reflector in itself, but then when the carbon nanotubes are sort of well distributed in the system, each nanotube reflects back, and this is reflected by the nearing nanotube, and so on, back and forth, it forms a fence. And this fence will actually not absorb, but it will attenuate the incoming electromagnetic radiation, which will appear as the material has absorbed all the electromagnetic signal falling on it. So multiple reflections and absorption is in high demand. So there is a class of material which is called RAM, radar absorbing materials. That means those materials which can absorb the radar frequencies are called RAMs. And these RAMs are in great demand not only in the commercial space but also in stealth application. And therefore these type of materials are very, very interesting. So let's slowly get on to some of the case studies. So let's pick one. Classical paper of PVC Pani, which is polyvinyl fluoride and Pani. This is a conducting blend, and PVC Pani has been blended so that the whole system becomes conducting. And to this, they have added graphene nanoplatelets, which is GNP. So polyaniline forms this thread-like structure in a PVC matrix, and if you are adding some graphene nanoplatelets, they also are in the Pani phase because of some specific interaction, and they also form a very nice network in the PVC matrix. So a combination of 15% Pani and 5% GNP put together can actually increase the conductivity significantly. As you can see, this is frequency in megahertz, and these are the AC conductivity, and these are the dielectric constant as a function of frequency. So what we see here is the conductivity keeps increasing as we increase the concentration of graphene nanoplatelets. That's because both are conducting and they give some synergistic effect. And at higher frequency, your conductivity is also very high, but this is 5 megahertz. But if you go to gigahertz, your conductivity may not be that high, so they tend to saturate at gigahertz frequencies. And so is the dielectric constant, so that also goes up. As you increase the frequency, you can see that the blue one has very high dielectric constant, about 5 up to 6. And this high dielectric constant materials would be very interesting in terms of absorbing or attenuating the electromagnetic radiation. So high conductivity and high dielectric strength is something which is very important when we are trying to design composites for electromagnetic interference shielding. So this is SE total, which is shielding effectiveness total in measuring dB. And you can see that when you go up in the frequency for a particular composition, as I mentioned with graphene nanoplatelets of 5%, you touch all the way up to 45 dB. Okay. So anything beyond 20 are commercially relevant because we know that 20 is the cutoff. 20 means attenuating of 99.99% of electromagnetic radiation. Anything above 20 in log scale means 99.9999 and so on. So 45 dB is a quite good figure, and this type of composites can be used for various applications. So now let's take a closer look of what all ingredients does this composite have, and let's see that when you have graphene nanoplatelets, since they are conducting, so each graphene nanoplatelets act as a reflector. So they reflect. Polyaniline is again conducting, so even they can reflect. So that therefore, the radiations or the electromagnetic signals back and forth reflect from these materials, and finally they are sort of attenuated because PVC is an insulating matrix and it will not contribute to shielding. So all the contributions comes from polyaniline and graphene nanoplatelets. Since both are reflectors, they reflect the incoming electromagnetic radiation within the composite, and thereby you see a shielding effectiveness of 45 dB. So that is one case study. The next case study is from my group. So what we have done is we took a system which is polystyrene and PMMA. So this particular system is sort of miscible in a common solvent, but they can phase separate when you evaporate the solvent. So for a particular concentration of PS-PMMA, we actually get a very nice co-continuous morphology. As you can see that this is an ASM image where PS is darker region, PMMA are lighter. So you can see threads of PMMA well connected within each other. So what we have done is we took carbon nanotubes, tried to functionalize them in such a way that they all prefer the PMMA phase. So if I now start filling my PMMA with carbon nanotubes, the entire system becomes conducting. So some of the zoom in SEM images show high dense network of carbon nanotubes in the PMMA threads. And in certain cases, you will see the carbon nanotubes also bridge from one domain to the other. In places where they are not interconnected, the carbon nanotube bridges. So which means all the electric current or the electrons can actually transport through this wire of carbon nanotube to the other phase and so on. So this jam network becomes quite interesting when we talk about shielding, and that's why what we see here is a little concentration of carbon nanotube of about 1% in a 50-50 blend takes you more than 20 dB of shielding. At the highest frequency, it was about 29 dB, which means it is a very good material. Now, if you carefully look at these case studies, carbon nanotube itself is a reflector, but when they are sort of dispersed in a matrix, they tend to become an absorber. But they're not absorber in a true sense. What they do is each carbon nanotube reflects, and therefore the electromagnetic signal is attenuated within the composites, and you see it as, it is manifested as that the composite is sort of absorbing all the electromagnetic radiation. So this is how blends with co-continuous structures could be very, very interesting in certain cases. So there are more examples which I will go a little fast. So these are EMA, ethylene acrylate, and EOC copolymers. It's a blend of these two, and carbon nanotube is added to this particular blend, and what you see is a co-continuous image where EOC has been etched out by hexane, and you can see nice co-continuous structure where one of the phases is continuous and the other phase, which is etched out, was also continuous. And now when you add carbon nanotubes, they all go to the EOC phase. So these are the domains, and you can see that the EOC phase is filled with carbon nanotubes inside. I'm sorry, so that the carbon nanotubes are located in the EMA phase because EOC was etched out to make sure that you have continuous phases. And these continuous phases filled with carbon nanotubes actually give very good conductivity and shielding. So you get conductivity of the order of 10 power minus 2 Siemens per centimeter for a particular concentration. E stands for EMA, O stands for EOC, and C stands for CNT. And as you increase the concentration of CNT, you keep going up in terms of conductivity and also in terms of shielding. So for a 15% of carbon nanotube, you hit all the way up to 35 dB. And if you break this total into two components, reflection and absorbance, so you see that the reflection goes down and the absorption goes up. So which means when a carbon nanotube forms a mesh-like structure, they actually tend to absorb all the incoming electromagnetic radiation through multiple internal reflection. Okay, but however, your current base VNA cannot distinguish multiple internal reflection and absorption, so it throws out output as absorption, but it's not absorption in a true sense. So what are we taking home from the first part of the lecture is we now understand that co-continuous morphology is very, very important, and a well-connected co-continuous structure can be stabilized by using nanomaterials, nanoparticles that can stabilize the structure, therefore there is no coarsening. The affinity of the conducting filler towards the continuous phase is again very important. The conductivity depends on the aspect ratio of the conducting filler. So higher the aspect ratio, lower is the percolation threshold, and higher is the conductivity. So the percent loading and the percolation threshold, there's a trade-off between these two, because if you keep going up in terms of concentration, at some point you get poor mechanical properties, and processing them becomes very, very tough. So therefore you need to find out the right composition where you do not compromise on the mechanical properties. So Pankaj, we can stop here for a while before we get on to the next part of the lecture.
We can take a 10 minutes break.
Sure. So if there are some questions here,
Sir, we can take it and end. No issue, sir. We can take first
at the end.
10 minutes.
Okay. Sure. Thank you.
Then, both sir, can we start then?
Sure.
Okay.
Okay, so let's move on to the next part of the lecture, which is on hybrid filler. So what we have just learned is by adding a single particle system like carbon nanotubes or graphene or maybe conducting polymer, we can actually develop materials or composites that can block electromagnetic shielding. But then you might have seen that the values are limited to certain dB, and the absorption is again limited to certain fraction. So how do we maximize it? Is by using some hybrid fillers where maybe one component is dielectric, the other component is conducting, or they are a combination of magnetic and conducting, or they are a combination of dielectric and magnetic, and so on. So why do we need hybrid fillers? Because we know that the impedance of each of these entities, if they are different, charge can be accumulated at the interface. So this interface becomes extremely important when we talk about electromagnetic shielding. And therefore, we need to make materials that can block electromagnetic radiations. And therefore, we utilize these kind of materials that have various or different characteristics. So in this part of the lecture, we will learn about these kind of hybrid fillers and see that whether using a polymer blend as a template, whether we can utilize hybrid fillers and develop materials that show very high shielding values. So this part of the lecture would again focus on carbonaceous nanofillers, both CMD and graphene. We will learn about interactions between the polymer and the particle and their effect on shielding. And we'll take a few case studies on hybrid fillers and see why they become or why they are so important. So among all the carbonaceous nanomaterial, graphene has been widely studied, and we know that graphene is called the building block of all carbonaceous nanomaterial because you can roll them, you can wrap them, you can stack them into various allotropes, and their extraordinary properties make them quite interesting. But what we are more interested is in the stacked material, and one such stack is graphene nanoplatelets or graphene oxide. So these materials can be utilized because you can play around with the high surface area that it offers. You can dope it with various ingredients so that you can create a hybrid material with a unique set of characteristics. Similarly, carbon nanotube, you can have both single wall and multi-wall, and the electronic properties of carbon nanotube depend on how is it folded, and therefore your EMI shielding properties also depend on the electronic properties of your carbon nanotube. So therefore, the way you fold it, you develop different electronic properties, and these electronic properties can be further harvested in actually making shielding material of different characteristics. So this is how we will focus more on these two carbonaceous material, carbon nanotubes and graphene, and we'll try to see that what happens if we dope metals, or we dope some ferrites, or we dope some dielectric or magnetic materials with graphene or carbon nanotube. How do we affect the shielding? So a combination of fillers to produce some synergistic effects is why we go with hybrid fillers. So combination of magnetic and electrically conducting fillers provide high electrical conductivity and sustaining magnetic hysteresis losses. So now you need to understand that if you want to develop a shielding material, you need more lossy materials. So what do we mean by lossy is, for example, carbon nanotubes are highly conducting, but they're also highly lossy. So they cannot be used to make batteries because they cannot store charge, but they can be used for materials where you need high electrical conductivity. So therefore, electrically conducting fillers are quite attractive. Similarly, if you have a magnetic material, you need to understand if this particular magnetic material has high loss. It could be hysteresis loss, it could be different kinds of domain losses and so on. So these materials are quite interesting from electromagnetic interference shielding point of view. So CNT, graphene nanoplatelets, carbon black are all sort of fillers that have been explored in the recent past for developing electromagnetic or EMI shielding materials. Fe3O4, the ferrite, which can impart magnetic properties, have been predominantly used because they also offer some multiple internal reflections. So ferrites, spinel ferrites, Fe3O4, alpha Fe2O3, all these materials have been doped onto graphene or carbon nanotubes to make hybrid fillers, and they can actually give you very high shielding as they are very lossy materials. One important thing you need to keep in mind here is as you move up on frequency, magnetic materials, because of Smoot's limit, have very, very low permeability. So therefore, magnetic materials are no good in shielding EM radiation at higher frequency. So if you are talking about gigahertz frequency, it is better that you work with fillers that are either conducting or dielectric, but not magnetic, because magnetic materials can shield EM radiation at lower frequency, mostly in radio frequency, but not in gigahertz frequency. So our group is also focusing on materials that are highly conducting or are dielectric, because these dissimilar materials can produce an interface where the accumulation of charge can take place, and this can block the electromagnetic radiation. So on one hand, we need seamless electrical fence where the electronic transport is seamless, and on the other hand, we also need these blocks, which are dielectric blocks, which will not let the electronic transport to go through, and that will accumulate charges at the interface is again what we need for blocking EM radiation. So let's take a look at systems like polycarbonate and sand. This blend is highly immiscible and it has been well studied. PC we know is a transparent system. It's engineering plastic. It's very brittle, but when you add sand, you can improve its ductility to some extent, and it can improve its impact toughness significantly. So to this particular system, if you add carbon nanotubes, you can improve the shielding to some extent. But as I said, that beyond certain concentration, you may not see very high shielding. And therefore, what we have done is we have doped Fe3O4 onto carbon nanotubes. So we functionalized Fe3O4 suitably so that we can graft it onto carbon nanotubes, and thereby they form some kind of a jam network where this carbon nanotube linked with a Fe3O4 and then again carbon nanotube, because it's a bifunctional entity. So these bifunctional entity, NH2, can also react with the terminal OH or COH groups of PC, so that your PC is sort of grafted on your Fe3O4 nanoparticles. At the same time, these Fe3O4 nanoparticles can also be grafted onto carbon nanotubes directly. So by doing so, we are trying to restrict the polycarbonate, we are trying to restrict the Fe3O4 in PC phase selectively. So that is the whole idea of grafting PC with Fe3O4, so that they are restricted in the PC phase, and the multi-wall nanotubes are sort of partially distributed in both the phases, but mostly in the sand phase. So then what you see here is a particular blend of 50-50, a different combination of carbon nanotubes and a hybrid structure. You see that the hybrid structures show higher shielding at lower concentration of carbon nanotube. So here, the concentration of nanotube is little lower than 3 weight%, and it still shows very high shielding. So just to recall that such shielding values were obtained at very high loading of carbon nanotubes, which makes processing these composites difficult, and therefore it is very important to achieve high shielding at relatively lower concentration of film so that we retain the integrity of the blends. We keep them intact, and processing is not a challenge in that case. So we also worked with doping Fe3O4 onto graphene oxide. So when you start with graphene oxide and you try to reduce iron salts onto this, in the process you end up in reduced graphene oxide because you consume some of the functional groups during the hydrothermal process. And in return, what you get is Fe3O4 is sitting on the vast surface area that the reduced graphene oxide offers. You can take a look at the high resolution TEM pictures. You can see these small dots on the sheet, which all corresponds to Fe3O4. So now you have to take a call whether to graft Fe3O4 onto CNT or to graft Fe3O4 onto graphene oxide. If you graft or if you dope Fe3O4 onto CNT, your aspect ratio of CNT gets reduced in this process. So therefore your conductivity might be adversely affected. So in order to avoid that, what we have done is we dope the Fe3O4 onto reduced graphene oxide sheet by hydrothermal technique and left the carbon nanotubes as is. So now a combination of these two during melt mixing results in a situation where the carbon nanotubes and the RGO Fe3O4 both are mostly in the PC phase, and there are of course some carbon nanotubes which migrated to the SAN phase as well, but mostly they are located in the PC phase. So then what we have noticed, at the same 3% concentration of carbon nanotube, we get much higher shielding value as compared to the previous case where the Fe3O4 were directly grafted onto carbon nanotubes. So there is a take-home message here that we should leave the carbon nanotubes as such so that its structure is retained. We don't dope it. Instead, you can dope this Fe3O4 onto RGO sheets. This would leave the carbon nanotubes as is, and thereby you can harness all the attractive properties that CNTs have to offer you. So similarly, what we have done is instead of ferrite, we started doping it with cobalt and nickel. So this is, I will not go into the details. So basically we have now cobalt oxide particles sitting on the reduced graphene oxide. And when we used a combination of CNT and reduced graphene oxide doped with cobalt, we reach about 35 dB at high frequency. So basically we have, we saw 3 different scenarios where the Fe3O4, the ferrite, is directly grafted onto carbon nanotube. You reach to certain dB. When you have a combination of RGO Fe3O4 and leave out Fe3O4 from CNT, you actually reach very high shielding values. And when you have cobalt, which is doped onto RGO and leave out CNT, you also reach minus 35 dB at 18 gigahertz, which is sort of very good in terms of commercial applications. So we moved on to some other systems to take a look, take an understanding that how different materials like barium titanate, the ferrite, how do they affect the shielding. So this is again a classical system of PVDF and ABS. So if you can guess, the PVDF ABS is highly immiscible system, and it is very difficult to compatibilize the system because they do not have any specific interactions between them. But there is a polymer which is mutually miscible to these two, and that is PMMA. So PMMA is miscible with PVDF, and PMMA is also miscible with ABS. So PMMA is mutually miscible to both the polymers, and that is how it can compatibilize this particular system. So what we have done here is CNTs were non-covalently modified with this perilene derivative, and then we tried conjugating barium titanate and Fe3O4 and try to understand that how this NH2 terminated barium titanate or Fe3O4, when it is grafted onto carbon nanotubes, how do the shielding actually affects. So if you take a look at these systems where we have 50-50 combination of PVDF ABS with different carbon nanotube derivatives. One is just modified with the perilene derivative, and this is the black one. And then we have barium titanate, which is coupled to carbon nanotube, is the red one, and Fe3O4 ferrite, which is again coupled to CNT, is the blue one. So at higher frequency, more or less, they have similar results, but at certain lower frequency, you could see a difference in terms of dB. So barium titanate is very good in the lower frequency region, but maybe the ferrites, which might overtake the barium titanate at much higher frequency, and therefore they might be good at very, very high frequencies. So from this understanding, or from this data, we have a clear understanding that if you dope or if you try to graft particles like barium titanate, which is a dielectric material, Fe3O4, which is a magnetic material, with carbon nanotubes, you can actually achieve very high shielding compared to when they are added separately in the system. So we also looked at different other combinations where we have PCPVDF filled with Pani and CNT Fe3O4, where we have polycarbonate, which is coupled with barium titanate at the beginning, and so on. So what we understand is, for a different combination of materials, like for example, multi-wall nanotube grafted with Fe3O4 and BT is separate, we get very high shielding all the way up to 60 dB. Sorry, I'm not here, I'm here. So up to 40 dB, close to 40 dB for a particular combination, and your dielectric constant significantly goes up at lower frequency. And your conductivity is sort of very, very high in the case of Pani CNT, but then they drop to a certain extent when you dope it. So our understanding here is that when the carbon nanotubes are doped with ferrite or with different other ingredients, your aspect ratio goes down and your conductivity drops. But such a drop in conductivity doesn't affect your shielding. So that's a second take-home message here, that although conductivity is a very, very important requirement, but it's not the only requirement of shielding. So basically, you need materials with the impedance mismatch, and therefore this variation in impedance would result in charge accumulation at the interface, and you get very high shielding. So I tried to pull out some literature from the state-of-the-art literature. So where people have used P.PSS, which is again a conducting polymer, and they have added graphite, or they have added carbon nanotube, which is doped with Fe3O4 particles, and so on. So all these hybrid materials can be converted into foams, it can be converted into films, and what you see here is the iron oxide nanoparticles are nicely decorated on the graphene sheet, and the carbon nanotube again is nicely decorated with iron nanoparticles or iron oxide nanoparticles, and so on. So these type of hybrid materials help you in many ways. One is iron oxide nanoparticles are not well dispersed in a polymer matrix if they are just added to the matrix. Instead, if you are doping this on to graphene oxide or carbon nanotubes, you not only improve its dispersion, but also end up designing hybrid materials which can be very, very interesting in terms of shielding. So this paper here reports about 90 dB of shielding for a particular combination of 3D structures of graphene, CNT, and Fe3O4 or Fe2O3 in this case with P.PSS. So these kind of hybrid structures are quite interesting for electromagnetic shielding applications. So if you have to compare these three cases, so you can see that in our group, we were able to reach close to 40 dB of shielding for a particular combination. But here, the concentration of CNT is only 3%. Whereas if you keep on increasing the concentration of filler, for example, here it is very high loading of carbon nanotube, then you can also reach very high shielding. But then processing is a challenge. So if you can overcome the processing challenges, we can actually go to very high shielding values at relatively lower concentration of filler. Because processing them at lower concentration of filler is very, very important, because at higher concentrations, you have many other challenges. For example, your composite might be very brittle, complicated shapes may not be possible, and so on. So these are some of the drawbacks if you increase the concentration of your hybrid materials. So again, if you take a look at the number of publications that come out of the hybrid fillers in the recent times, if you see there's a surge in terms of publications. Okay, so the red curves is this side, this is publication per year, and the black curves are on this side. These are the number of publications. So if you see only EMI shielding, then you have numbers reaching as high as 3,000. If you break it down to health effects, only shielding, some interference or field safety, you see that the number of papers per year is still going up. So we also have, as I have shown you, that in the case of EMI shielding with polymer blends, mostly with foams, again you see that the number of papers in recent times have gone up. So polymer composites for shielding also has gone up, as we have seen in the first part of the lecture. So more and more people are researching on materials and hybrid materials for shielding and trying to achieve very high shielding effectiveness at relatively lower concentration of fillers. They're also trying to make foams or porous structures, or trying to make some multi-layered architecture, because these type of materials can help in multiple internal reflection, and this would eventually result in very high shielding values. So meshes again are very important. We know that metal meshes are very interesting because I gave you one example of carbon fiber mesh which is stuck onto microwave door. Similarly, if you have a metal mesh, all the incoming electromagnetic signal will just bounce off the surface, and because of very small skin depth, they are mostly reflected. Whereas if you have a composite material, you can utilize the properties of multiple internal reflections by using these hybrid materials. So in the recent times, materials that are transparent and yet which show high electromagnetic interference shielding are in great demand, and therefore people have moved on with silver nanowires or carbon nanotubes dispersed in such a way that it doesn't affect the optical transparency and yet give very high shielding. Because so that you can use these as paint or coating formulations on precise electronics without even being noticed. So if it is transparent yet conducting and good shielding values, so you may not notice the protective coating that is on precise electronic devices. So paints and coatings are the next generation material. So you need to develop a morphology on the surface after this coating so that they form a co-continuous structure and yet retain the optical transparency and show very high shielding values. So this is where the research is headed to. More and more materials are being discovered, and people are trying to develop formulations that can be coated, that can be made into foams, or that can be made in terms of mesh, the 3D printed structure, which is also the theme of this workshop. So a lot of research is going on 3D printed mesh that are highly conducting, non-metal. These are all made out of polyurethane or polycaprolactone or polylactic acid and so on. And these conducting meshes are being used as a shielding material for a variety of applications. So that is where the research is moving forward to. And even we have started working with 3D printed polyurethane structures, and we try to incorporate graphene and hybrid fillers in the system so that we have this very lightweight mesh, and we keep an eye on the mesh size, which should be less than a millimeter so that electromagnetic radiations do not pass through. If it is more than millimeter, then they actually pass through, and which is of no use to us. So you can actually develop, using 3D printing, different types of topographies on the surface. So that these topographies can also help you in multiple scattering, which is a key to attenuate the electromagnetic radiations. So that is all from my end. And let me thank all the funding agencies that have generously funded us for all the research that I've shown that came out of my lab. More particularly SERP and DST, which have funded, and our institute also is quite generous in funding new facilities so that we can now expand. So when we started with expand frequency 8 to 12 gigahertz, and now we have reached all the way up to 26.5 gigahertz, and we have different waveguides which can help us in understanding the shielding mechanism for different or for a wide range of frequency. So that's all about from me. Thanks for your patience, and if you have any questions, I'll be happy to answer them.
So audience, you can unmute yourself and ask questions. I think if there are no questions.
Yeah, I have a question.
Yes, okay.
Yeah, myself
Yes.
Shrikant.
Yeah, hi Shrikant.
Yeah, so I have two questions. One is, as you discussed, there are three mechanisms that is responsible for total shielding effectiveness: reflection, absorption, and total internal reflection. So which is the most dominating combination for highest total shielding effectiveness? And secondly, what are the commercially available materials for EMI shielding in markets or the current scenario?
Okay, so to answer the first one, till date, most of the materials that are commercially available are all metal based, like metal mesh or some foams and so on, and they are primarily reflectors. But the problem with these reflectors are that if a particular material is shielded with a reflector, all the incoming electromagnetic radiation is bounced off its surface, but then they go and interfere with the neighboring electronics. So therefore, there is a need for materials that can actually absorb electromagnetic radiation. And when we say it absorbs, it will then has to dissipate this energy in terms of heat, and therefore your material also has to be good thermal conductors. So certainly, reflectors are not a good choice, but the commercial market is dominated with all reflector materials because people are still trying to see or trying to design that those materials that can block or absorb electromagnetic radiations. Now coming to your second answer, there are of course aluminum and copper based meshes, and there are also copper silver paints that can block electromagnetic radiation. Most of the solutions are again dominated by metals. Very recently, people have understood that metals have certain disadvantages like their weight, corrosion, and so on. And therefore, they are moving away from metals and trying to focus on polymer composites in various forms. It could be polymeric foams, it could be multi-layered structures, or it could be films, and so on. And when they're researching on polymer composites, they have learned that single particle system, like for example, only carbon nanotubes for that matter, may not be sufficient or may not be enough to block electromagnetic radiations at all frequencies. And therefore, there is a need for hybrid. So certain startups in Delhi have already started commercializing polymer-based materials for blocking electromagnetic radiation. So modern days, you will also see laptop pads. So you can actually keep that pad on your lap and start working without any challenge from the electromagnetic radiation that is generated from the laptop. There are materials like foams that are used to protect the radar from external pulse of electromagnetic radiation, and these are made out of ferrite filled rubber and so on. So people are moving out from commercial or conventional materials to more polymer based solution.
Yeah, thank you very much.
Thank you, Srikanth. Are there any other questions?
I think I will just ask one general knowledge question. There are research on a radar absorbing material. So what is your opinion on that research part we can take and then again put it for mobile or some other applications, commercial applications? What is your take on it?
Radar absorbing materials actually are required for stealth applications which operate at much higher frequency. For example, military radars operate at 80 gigahertz, and the commercial radars operate at about beyond 5 gigahertz all the way up to 26 gigahertz. So materials that can absorb electromagnetic radiations at those high frequencies may not do the same job for mobile phones, which operate at 2.45 gigahertz for 4G and maybe slightly above 3 in the case of 5G. So materials for a specific frequency whereas conducting materials are good at almost all frequencies, but we need to understand that if the conducting material is not dispersed well, it doesn't provide that electrical fence that is required. And then we also understood that only conducting materials may not be helpful, and therefore we need to add some hybrid where we get a combination of dielectric and conducting and so on. Only dielectric materials may not be good for certain frequency band, but might be good for higher frequency band. And in the ferrites, you can actually tune the frequency band by doping with various entities and so on. So there are a whole range of materials which work at different frequency. So based on the frequency, you can now try and dig out information that, okay, for this frequency window, which material would be better. But certainly radar absorbing material which work at very high frequency may not be very good for mobile applications. Having said that, there could be a material which works at 3.5 gigahertz for phones all the way up to 80 gigahertz as well. So people are still trying to understand how best we can design a material that can work in a wide band of frequency.
Thank you. So is there any questions? We can take one more question. Okay, I think there are no questions. So what I will do is I request Dr. Bose to stay with us for some more time. So what I will do is I will just overall thank brief about our workshop. Thank everyone.
Sure.
And with Professor Bose few notes, then we can end up the session.
Sure.
Okay. So thank you for accepting my invitation, sir. So first of all, I thank management, Vice Chancellor, sir, Registrar, sir, Dean, the School of Mechanical Engineering for giving me opportunity to conduct this workshop of advances in material processing and in combination with 3D printing and opportunities. Okay. I thank also my coordinator, Dr. Ambuj Sharma, to help me. And I thank all my research scholars also agreed to join this workshops. I thank all the invited speaker to accept my invitations and giving the nice presentations, which can help the participants to think uh, how this advanced materials and its processing, how they can implement in 3D printing. So I will just give a brief about what are the different sessions from first day to third day. So the first session was taken by Dr. Divya Padmanabhan. She talked about, in general, about the additive manufacturing in detail, which set up a good note to start with the workshop. Thereafter, Dr. Vijay Hivarkar from DIIT Pune talks about the metallurgical aspects of 3D printing, and then how to develop a product for defense industry. And then Dr. Rajesh Khatrikar talk about the characterization of the material, and in specific to 3D printing, how to characterize the microstructure. In second day, Dr. Shashi Bhushan Arya talk about uh, corrosion aspects of additive manufactured product. In general, he talk about the corrosion too. And thereafter, there was a talk given by Dr. Ravindra Manikanta on 4D printing. And then Dr. M.S. Shrikant, who is currently with us now, he talked about, in general, about these polymer processing and some 3D printing case studies. And then a final talk was given by Dr. Ravi Kumar V. It was an exhaustive talk. What are the different opportunities in 3D printing? So he also talked about how to develop our own machines for a 3D printing. And of course, he has given the information. He is developing a 3D metal printer, 3D FDM, and other printers in his lab at IIT Jammu. And what are the different opportunities, artificial intelligence and other emerging areas. So additive manufacturing can go in a smart way. And the third day, the morning session was supposed to be taken by Dr. Arifur Rahman, but due to some urgent work, he requested me to take his session, and he has given me some slides too. So I have taken the first sessions for today's on these polymer nanocomposite, and especially on interface aspects. And then Dr. Akash Mohanty has taken a session on epoxy nanocomposites, and specifically inside the epoxy, how to achieve nanoparticle reinforcement in situ. And thereafter, I talk about polymer blends and its nanocomposites, which set up some tone for Dr. Surya Sarthi Bose talk. And Dr. Surya Sarthi Bose given a very nice talk about the polymer blends, control of microstructure, various case studies from his group and other literature, and this state of art of EMI shielding research ongoing and the future prospects. And he also has given the direction about the 3D printing, which is the upcoming area. So I can say that this workshop, it has given the highlight about the advanced material processing, as well as the 3D printing opportunities. With the basics of 3D printing was covered. With that note, I thank all the participants who agreed to participate in this workshop. I hope this workshop is very useful for them. And even this is a good learning curve for me also to conduct the workshop. I thank everyone, and I request Dr. Shujo to give his final word for this workshop.
Thank you, Pankaj. So I will leave a message with you that 3D printing, which is an emerging area, has many dimensions, not only from design perspective, but also from composite viewpoint. So people are moving towards 3D printing instead of making forms by chemical or by any other method for that matter, because again the turnaround time is less and therefore industries are more interested. So you can quickly develop a mesh-like structure within minutes by 3D printing. And therefore many areas are actually moving towards additive manufacturing in a big way, as Pankaj said. So composite field was a little lagging behind, but it is picking up now because we have certain limitations in polymer 3D printing, because either you have to go with a powder bed or you have to go with a spool. And if you're working on composites, again, spools are difficult to be made, and then there are other challenges in the spool. Powder is again difficult to be made in such large quantities and so on. So there are new 3D printers that are coming up in the market, which has multiple extrusion head. So where you can now dump your polymer composites and they can print it for you. But then people are facing challenges like the right kind of viscosity, the right kind of stickiness in the composites, which is causing other issues. But I'm sure in the near future, you will have printers that can actually print various designs of polymer nanocomposites in a different setup. And I have seen a printer with multiple extrusion heads, which means you can have multiple components being extruded at the same time. So this way you can generate multi-component systems within no time using a 3D printer, and various shapes which are difficult from conventional methods can actually be developed. One such area is the surface topography, which is very much required for electromagnetic shielding, can be very well designed using a 3D printer. So you can have pyramids, you can have different surface topography on the surface, so that each matrix can actually help in shielding electromagnetic radiations in many ways. So it's a long way to go, but I can see that very soon we will have printers that can print composites in large scale, so that you can eventually be able to print a complete radar with a composite material, and these composite radars can be used, which can act as a or block electromagnetic signals, which currently we are doing using a paint, can be done using a 3D printed structure. So though it's a long way to go, but it's a good start. Thank you.
Thank you, Dr. Suryasathi Bose, for giving us the valuable solution and the current insight. So we
Thanks,
can
Pankaj.
wind up the full workshop now. Thank you, everyone.
Thank you. Bye-bye.
Thank you.